Welcome, friends! He is so glad they are here. Whether they are drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, they have found the right place. Before the journey begins, he would love to know where in the world are they listening from. Perhaps they are wrapped in a blanket sitting by a softly lit window or resting somewhere under an open sky. Wherever they are, he hopes they are warm, comfortable, and ready to wander with him into atoms, those tiny worlds once imagined as simple beads, now known to be layered with structure, probability, and deep quiet complexity. If they find peace or curiosity in these gentle stories, he invites them to consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who have already joined along, thank you. The voice remains whisper soft, and the first image is the most ordinary one, a hand resting on the stone, a fingertip touching a granite countertop, a rough wall, a river pebble. The surface feels continuous, firm, unquestionable. Yet the accepted fact beneath that firmness is that matter is made of atoms, and atoms are not tiny solid spheres. They are structured systems, governed by quantum mechanics, with electrons occupying quantized energy states around a nucleus, and with the apparent solidity of matter arising from electromagnetic interactions and the Pauli exclusion principle, rather than from physical contact in the everyday sense. Only took a few centuries for the little hard ball to dissolve into a cloud of probabilities and rules. The narrative slows and lingers on the scale change. A granite rock is a mosaic of mineral grains, each grain a crystal lattice, and each lattice a repeating arrangement of atoms held by bonds. Those bonds are not miniature hooks, they are outcomes of electron behavior in quantized orbitals and shared electron densities. In quartz silicon, an oxygen link in a framework. In feldspar, aluminum substitutes for silicon and requires charge balance. In mica, layers form because bonding strength differs between sheets. This is accepted mineral chemistry. The periodic table and quantum bonding determine what kinds of minerals exist and how they assemble. A poetic detail appears in the way crystals can record growth, zoning faint bands of composition that reflect changes in temperature and chemistry during crystallization like subtle rings inside a stone tree. Only took atoms choosing where to sit in a lattice for a crystal to carry a faint diary of its own birth. The narrative keeps the emotional tone flat and contemplative. It notices that atoms are small enough to be invisible, yet their behavior is strict enough to shape continents. Electrons, which cannot be pictured as tiny planets circling a nucleus in neat orbits, still arrange themselves into orbitals, probability distributions whose shapes can be described mathematically and whose filling rules create the periodic table's logic. The accepted fact is that atomic spectra, chemical reactivity, and bonding patterns arise from quantized electron states. This is why sodium reacts eagerly with water, why neon remains inert, why carbon forms chains, why iron changes oxidation states, why oxygen binds strongly. Only took electrons refusing to occupy the same state for chemistry to have personality. The ironies arrive softly. 3 small, dry observations that do not change the calm. The first irony is that the hardest rock on Earth is mostly empty space at the atomic level, with nuclei separated by vast distances compared to their size. The second irony is that solidity, the feeling of contact, is mostly electromagnetic repulsion, and quantum rules preventing electrons from overlapping rather than the touching of solid objects. The third irony is that the more accurately atoms are described, the less they resemble anything intuitive, and yet the description predicts reality with remarkable fidelity. Only took reality being strange to be the reason it can be understood. The narrative now moves inward to the nucleus, not with drama, but with quiet precision. An atom's nucleus contains protons and neutrons bound by the strong nuclear force, and the number of protons defines the element. This is accepted. Yet even here what appears simple becomes layered. Protons and neutrons are not fundamental in the deepest sense. They are made of quarks held by gluons, and their mass is largely the energy of binding and motion, rather than the sum of quark masses. This is accepted in particle physics. Most of the mass of ordinary matter arises from quantum chromodynamics, dynamics not from bare constituent masses. Only took empty-looking particles to be mostly energy in disguise. The narrative remains grounded by tying this to Earth. The mass of Earth, the weight of oceans, the pressure at the core, all depend on this deep fact that matter's mass is emergent from binding energy. The planet's gravity is shaped by mass, and mass is shaped by forces at scales too small to see. A gentle modern analogy can hover restrained, like a crowded room's weight being more about the collective movement and tension than the individual's shoes. The mass of a proton is more about the field energy inside it than the quarks alone. Only took a metaphor to get close and still not fully capture it. The section holds a quiet scientific mystery early, because atoms remain not fully simple even now. Quantum mechanics is extraordinarily successful, yet it contains unresolved foundational questions. What exactly does the wave function represent, physical reality or knowledge? Why do outcomes appear probabilistic? How does measurement produce definite results? These are interpretation-level uncertainties, not failures of prediction, but they are real and active in philosophical and sometimes scientific debate. Atoms in practice behave according to the equations, yet the meaning of the equations remains partly unsettled. Only took the most successful theory in science to still leave room for questions about what it means. The narrative stays with the atom's quiet structure. Electrons occupy shells and subshells, and these fill according to quantum numbers and energy minimization. The shapes of orbitals SPDF are solutions to the Schrödinger equation for hydrogen-like systems modified in multi-electron atoms by shielding and electron-electron interactions. This is accepted chemistry as the many-body problem made practical through approximations and computational methods. Even a simple atom beyond hydrogen requires complex calculations to model precisely, and yet the periodic table gives a robust framework. Only took one electron being added to make the math much harder, and nature does it effortlessly. A lesser known detail rests in the fact that many properties of atoms in solids are collective rather than individual. Electrons in a metal can behave as delocalized bands, not as belonging to one atom creating conductivity. In semiconductors, band gaps arise from periodic potentials and quantum states spreading across a crystal. In minerals, color can come from trace impurities and defects, tiny changes in electron energy levels that alter light absorption. For example, small amounts of iron can color quartz, and radiation can create color centers in some crystals. Only took a missing electron in the right place to make a gemstone change color. The narrative keeps that detail as a soft reminder. Atoms are not isolated. They are influenced by neighbors, by fields, by temperature, by pressure. Under high pressure, electron orbitals can change, altering mineral structures and stability. Deep in Earth's mantle, minerals transform into higher pressure phases because atomic arrangements become more compact. This is accepted mineral physics. Olivine becomes Wadsleyite and ringwoodite at certain depths. Perovskite-structured minerals dominate deeper. The planet's interior is therefore an atomic story told by pressure and temperature. Only took pressure squeezing atoms closer for the mantle to change its mineral identity. The narrative maintains one uninterrupted flow and returns to the everyday again because the series remains a meditative journey grounded in truth. A breath is taken and the air itself is an atomic mixture, mostly nitrogen and oxygen molecules colliding exchanging energy following Maxwell-Boltzmann distributions that describe speeds and temperatures statistically. Temperature in this view is not a substance. It is a measure of average kinetic energy, a statistical summary of countless atomic motions. This is accepted thermodynamics and kinetic theory. Only took billions of collisions per second for warmth to feel smooth. And within those collisions, quantum rules still matter. Rotational and vibrational modes are quantized, influencing heat capacities and spectra. The world's simple warmth is quietly quantum too. The section closes by letting the atom remain both familiar and strange. It is the building block of rock, air and water, yet it is not a bead. It's a structured system of fields and probabilities with mass that emerges from binding energy with electrons that occupy shapes rather than tracks, with behavior that is predictable and yet fundamentally probabilistic in outcome. The planet's deep history, its cooling, its differentiation, its oceans, its life depends on these tiny worlds behaving consistently, and the quiet mystery remains like a dim starlight behind the science. Why the rules are this way, why atoms exist with such stability, and why the universe allows matter to be both orderly enough to build a world and subtle enough to never be completely simple. The stone beneath the fingertip remains solid, but the narrative now lets the atom story drift outward in time, because Earth's atoms are not born on Earth. The accepted fact is that the lightest elements, hydrogen and helium with trace lithium, form primarily in the first minutes after the Big Bang, while most heavier elements form later through stellar nucleosynthesis and explosive events such as supernovae and neutron star mergers. Earth's iron, oxygen, silicon, carbon, calcium, and every trace metal are in that sense the settled ash and condensed breath of earlier stars. Only took a universe cooling for a few minutes to set the first ingredients, and then billions of years of stars burning to supply the rest. The narrative remains whisper soft and keeps imagery elemental, a cold molecular cloud in the galaxy dust drifting gas thin and wide, gravity gathering it slowly. Within that cloud, the elements are present as atoms, sometimes as molecules, sometimes frozen onto dust grains. This is accepted astrophysics. Interstellar medium contains gas and dust with chemistry occurring on grain surfaces, including the formation of molecular hydrogen and more complex organics in certain environments. A lesser-known detail rests in the fact that interstellar dust grains can develop icy mantles. Water ice, carbon monoxide ice, methanol, ice where simple and complex molecules form under ultraviolet irradiation and cosmic rays. These grains become tiny laboratories, cold and dark, where atoms stick, react, and occasionally return to gas. Only took a grain smaller than a hair to carry a mantle of ice and chemistry across light years. The narrative then moves into the interior of stars, because this is where simplicity becomes layered complexity. In stellar cores, hydrogen fuses into helium, releasing energy. In more massive film stars, helium can fuse into carbon and oxygen, and successive burning stages can build elements up to iron through processes like the alpha process and silicon burning. This is accepted. Fusion in stars produces elements up to iron group because beyond iron fusion does not release energy. The path is not uniform across all stars. It depends on mass, temperature, density, and evolutionary stage. Only took gravity squeezing a core to ignite fusion, and then fusion becoming the star's way of holding itself up. Yet Earth's most common elements are not all made by simple fusion chains. Carbon, for example, forms in stars through the Tor's triple alpha process, a delicate reaction where 3 helium nuclei effectively combine to make carbon. The accepted detail is that this process is facilitated by a resonant excited state in carbon-12, often called the Hoyle state, which makes carbon production in stars efficient enough to account for observed abundances. This is a real and celebrated example of how nuclear physics details shape cosmic chemistry. A poetic detail lingers in the fact that a particular energy level inside carbon-12, an invisible resonance, influences whether the universe becomes rich in carbon and therefore capable of organic chemistry at scale. Only took one nuclear energy level being just so for carbon to be abundant, which is quietly unsettling in the gentlest way. The narrative does not dramatize, it simply notes. Here the section's quiet mystery appears naturally. Why do nuclear and fundamental constants take the values that allow such resonances and stable nuclei? Physics measures these constants and can model consequences of changes, but it does not yet explain their values from first principles in a way that satisfies all questions. The Hoyle state often becomes part of anthropic discussions, but the narrative remains strict and scholarly. It is a point of sensitivity, not a proof of intention. Only took one resonance to invite philosophical questions that remain unresolved. The narrative continues into the making of elements heavier than iron, because this is where atoms truly stop being simple products of steady burning and become artifacts of rare conditions. The accepted fact is that heavy elements beyond iron are produced mainly by neutron capture processes, the slow process S process in certain evolved stars such as asymptotic giant branch stars, and the rapid process R process in environments with extremely high neutron flux, such as neutron star mergers and some types of core collapse supernova. The relative contributions of these sites to different isotopes are an active research area, but the broad framework is accepted. Only took neutrons arriving in floods or trickles for gold iodine uranium and many other elements to exist at all. A lesser-known detail rests in this process itself. It occurs over long timescales in stellar interiors where neutrons are released by specific reactions, and because neutron capture is slow, relative to beta decay nuclei, move along a path near the valley of stability. This means the pattern of heavy element abundances carries a signature of nuclear half-lives and cross-sections, tiny probabilities that determine cosmic inventory. Only took a nucleus being slightly more likely to capture a neutron to shape the abundance of a metal on Earth. The narrative then touches the R process, because it is both real and still partly mysterious. In the R process, neutron capture happens so quickly that nuclei are driven far from stability before decaying back, producing a characteristic pattern of abundance peaks. Observations of kilonovae, transient events associated with neutron star mergers support heavy element production in such events, and the detection of gravitational waves from a neutron star merger with electromagnetic counterparts has strengthened this connection. This is accepted in modern astrophysics, yet uncertainty remains. Are neutron star mergers the dominant source of our process elements in the early galaxy given their rates and delay times, or do some rare supernovae contribute significantly, especially at very low metallicity? The quiet mystery is one of timing and site diversity, how the earliest heavy elements appear in the galaxy's first generations of stars. Only took a few ancient stars with odd abundances to keep the origin story of some elements debate. The narrative remains grounded by turning back toward the solar system's formation environment. The atoms forged in many stars mix into the interstellar medium, and later, a region of that medium collapses, forming the Sun and a protoplanetary disk. Earth's material is therefore a blend of contributions from different stellar sources mixed and reprocessed. A poetic real-world detail rests in pre-solar grains found in meteorites, tiny mineral grains that predate the solar system identifiable by isotopic anomalies that do not match solar composition. These grains can come from supernovae red giants and other stellar sources, and they survived the solar system's formation to be found in laboratories. Only took a grain surviving formation and impact and heat to carry an isotopic accent from another star. The narrative lets this detail rest as an anchor Atoms are old, and some grains are older still, carrying proof of their birthplaces in isotopic ratios. The ironies arrive softly dry and slow. The first irony is that atoms are often introduced as the simplest building blocks, yet their origins require some of the most extreme environments in the universe. The second irony is that the rarest events, explosions, mergers seed the most familiar materials are, so that a wedding ring and a mountain share ancestry in catastrophe. The third irony is that humans search for meaning in cosmic coincidences, yet many of the sensitivities in nucleosynthesis are simply facts of physics that do not come with explanations attached. Only took the universe having parameters to make those parameters feel significant. The narrative now gently ties stellar forging back to Earth history, because Earth's transformations depend on which elements exist and in what ratios. Iron's abundance enables a dense core and a magnetic field. Silicon and oxygen dominate the mantle and crust, forming silicate minerals. Carbon and nitrogen allow organic chemistry and atmospheric cycling. Uranium and thorium provide long-lived radiogenic heat. These are accepted connections. Earth's internal heat budget includes radiogenic contributions, and its differentiation depends on element partitioning. The quiet scientific mystery is that, while these broad connections are known, the exact initial composition of Earth, including volatile inventories and oxidation state, remains uncertain and is still refined through meteoritic comparisons and isotope systematics. Only took planets forming from mixed dust to make initial conditions a forever question. A gentle modern analogy can hover like baking, with ingredients gathered from many kitchens. The final cake's flavour depends not only on the recipe, but on what exactly ends up in the bowl. The analogy remains soft because Earth is not baked, but it captures the idea that formation is mixture and selection. The narrative closes the section by letting the cosmic scale fade into the immediate, again the atoms in a breath, in a glass of water, in a basalt cliff. All carry ancestry in stellar interiors and explosions. They are not simple. They are the end of long chains of nuclear reactions, sensitive to resonances, and feel lives shaped by rare events and common burning. The planet's latest recooling ocean's life rests on this ancient inventory, and the quiet mystery remains still unforced: why the universe's parameters permit such rich element making at all, and how exactly the rare and common sources of heavier elements combine across time to produce the specific palette that becomes Earth. The atoms forged in distant stellar interiors do not arrive on Earth as a neat inventory. They arrive as dust and gas mixed and drifting, and the narrative lets that drift become the next transformation. Because between element making and planet making, there is a long, quiet stage where simple collisions build complexity, one contact at a time. The accepted fact is that the solar system forms from a collapsing molecular cloud that becomes a rotating protoplanetary disk around the young sun. And within that disk, dust grains collide, stick, grow into larger aggregates, and eventually participate in the formation of planetesimals and planets. This is supported by observations of disks around young stars, by meteorite ages that cluster around the solar system's beginning, and by models of disk evolution. Only took gravity gathering a thin cloud for a whole architecture of worlds to begin slowly, without any announcement. The narrative stays whisper-soft and imagines the disk not as a flat picture, but as a volume of motion gas flowing inward, angular momentum carried outward, dust grains settling toward the mid-plane where collisions become more frequent. In the cold outer regions, ices coat grains, increasing stickiness. Closer in, higher temperatures drive off volatiles, leaving more refractory materials like silicates and metals. This temperature gradient is an accepted feature in disk physics, often described in terms of condensation fronts or snow lines, where specific materials transition between vapor and solid. A lesser-known detail rests in how the water snowline and other snowlines for compounds like CO and CO2 can influence where solids concentrate and how quickly bodies grow, because ice-coated grains stick and grow differently than dry grains. Only took a narrow ring in a disk where water freezes to change how fast the building blocks can assemble. The narrative then lingers on the most delicate step in planet formation, because here the atom's story becomes a story of surfaces. At microscopic scales, grains can stick through van der Waals forces, and electrostatic effects and porous aggregates can grow by gentle collisions. Yet as bodies reach centimetre to metre sizes, many models encounter a barrier. Collisions become more energetic and can lead to bouncing or fragmentation, and aerodynamic drag can cause radial drift, spiralling solids inward toward the Sun on timescales that can be short compared to growth. The accepted fact is that radial drift is a significant issue in disk dynamics, and that simple sticking alone struggles to explain the leap from pebbles to kilometre-scale planetesimals. This is the section's quiet scientific mystery: how exactly the disk's small solids cross the gap to become large gravitationally bound bodies quickly enough to survive and seed planets. Only took a metre-size rock feeling drag to threaten the entire construction project. The narrative remains calm and notes that several plausible mechanisms are actively studied. One leading idea involves the streaming instability, where interactions between solids and gas can cause pebbles to concentrate into dense filaments that gravitationally collapse into planetesimals. This mechanism is supported by simulations and is widely discussed as a promising route past the growth barriers. Though the exact conditions needed, solid-to-gas ratio turbulence levels, particle sizes, remain topics of research. Another possibility involves pressure bumps and vortices in the disk that trap particles, reducing drift and enhancing growth. Yet no single pathway is confirmed as the only route, and the true disk likely uses several. Only took a disk being slightly lumpy rather than perfectly smooth for solids to find safe harbours and gather. The narrative keeps Earth in view by remembering that the building blocks that survive become meteorites, and meteorites are records of early solar system processing. The accepted fact is that many meteorites contain chondrules, millimetre-sized spherical droplets of once molten silicate that cool and solidify quickly embedded in a fine-grained matrix. Chondrules are among the oldest solid materials formed in the solar system, and their textures show rapid heating and cooling events in the disk. Yet their origin remains partly uncertain. Proposed mechanisms include shock waves, lightning-like discharges, and heating near the young sun followed by transport. The mystery here is specific and quiet: what exactly melts chondrule precursors so frequently and so uniformly across regions, and how those droplets mix and accumulate into larger bodies. Only took the early disk being energetic to leave behind tiny melted spheres that still do not fully explain their own furnace. A poetic detail rests in a way. Chondrules look like tiny frozen raindrops of rock, each one a small world with its own crystal textures, barred olivine patterns, radial pyroxene needles formed as molten droplets cool in seconds to minutes. These textures can be read like cooling histories written by atoms choosing lattice positions as heat leaves. Only took a droplet cooling in a gas disk to create a miniature landscape of crystals. The narrative then widens to the formation of planetesimals, because once kilometre-scale bodies exist, gravity changes the style of growth. Bodies collide and accrete, forming larger objects. Some collisions are gentle and additive, some are violent and disruptive. Over time, differentiation can begin inside larger planetesimals, when short-lived radionuclides like aluminum-26 provide heat-melting interiors and allowing metal and silicate to separate. This is accepted. Many differentiated meteorites come from early formed bodies that heat and segregate. The early solar system is therefore not only a place of assembling, It is a place of melting, sorting, and reassembling, already rehearsing what Earth will later do on a larger scale. Only took a radioactive isotope with a short half-life to turn some early rocks into small hot worlds with cores. The ironies arrive softly dry and slow. The first irony is that planet building begins with dust so fine it would feel like smoke, and yet it ends with worlds heavy enough to bend space with gravity. The second irony is that the early disk is a place of both construction and destruction, with collisions that build and collisions that erase, as if stability is something that must be earned by mass. The third irony is that the planet's future solidity depends on processes that are almost absurdly delicate at first. Grain surfaces meeting gently before they become brutally energetic. Only took a quiet sticking force to start something that later involves giant impacts. The narrative remains grounded and approaches the chemical sorting that happens before Earth exists. In the inner disk, high temperatures favour refractory solids, calcium aluminum-rich inclusions, or CAIs, form as some of the earliest condensates. CAIs are found in certain meteorites and are among the oldest dated solids in the solar system. This is accepted. CAIs define time zero for many solar system chronologies. The section does not repeat numbers. It simply holds the idea that some solids condense early and carry isotopic anomalies, including evidence for now extinct radionuclides. A lesser-known detail rests in the oxygen isotope variations seen in different solar system materials, which suggest complex mixing and photochemical processes in the disk. Oxygen isotopes in meteorites do not follow simple mass-dependent fractionation lines. They can form distinct trends that still require careful explanation. This remains an active area of research tied to processes like self-shielding and CO photodissociation and mixing between reservoirs. Only took oxygen having 3 stable isotopes to complicate the disk's chemistry in ways that still invite debate. The narrative keeps a gentle modern analogy restrained like flour and sugar that look uniform until moisture and heat reveal different behaviors. The disk's gas and dust contain hidden chemical tendencies that emerge at different temperatures and pressures. The analogy stays soft because disks are not kitchens, but it helps the mind accept that conditions select outcomes. Only took a few hundred degrees of difference across distance to decide whether a planet starts wet or dry. The quiet scientific mystery returns in a larger form: how Earth acquires its volatiles water, carbon, nitrogen, and when. Some models favour delivery by hydrated asteroids from beyond certain snow lines. Others emphasise retention of nebular gas and local adsorption. Still others combine sources. Isotopic evidence, such as hydrogen isotopes in Earth's water, compared with various meteorite classes and comets, provides constraints, but not a single simple answer. The narrative holds this uncertainty as part of the disk's story. Formation is mixture, and mixture leaves signatures that can be partially read. Only took water being both common and mobile to make its delivery path complex. The narrative returns to motion because disk motion is the quiet sculptor. Turbulence stirs particles, gas drag sorts sizes, resonances and gravitational interactions shape orbits. Over time, the young sun's radiation and winds can disperse the gas disk, ending the era of easy damping and leaving a system of solid bodies that interact more violently. This is accepted. Protoplanetary disks dissipate on timescales of a few million years in many observed systems, though the exact timing varies. Once gas is gone, planets and embryos continue to collide and accrete, but now without the same gentle cushioning. Only took the gas thinning away for the system to become louder in collisions. The section ends by returning to the smallest scale again as a soft callback to the project's title. Atoms once forged in stars become grains, grains become pebbles, pebbles gather into planetesimals, planetesimals collide into embryos, and somewhere in that slow hierarchy, Earth's material begins to exist as a distinct collection of matter, not yet a planet with oceans, but already a body with a destiny shaped by chemistry and gravity. The world that will later feel continuous under a fingertip begins as countless discrete contacts, one grain sticking to another, one droplet cooling into a chondrule, one cluster collapsing under its own gravity. The narrative leaves the central uncertainty unresolved, calm and honest. The exact route from dust to planetesimal remains one of the great technical mysteries of planetary science, and the details of volatile delivery remain an open ledger. Yet the transformation itself is undeniable in outcome. Earth exists because the tiny worlds of atoms, through forces both gentle and vast, learn how to assemble into a larger world without ever becoming truly simple. The disk's dust has already learned how to gather, and now the gathered bodies learn a harsher lesson. Size brings heat, and heat brings sorting. The narrative remains whisper-soft and settles into the young Earth as a mass that is no longer a gentle aggregate of pebbles, but a growing world where impacts add energy, radioactive decay releases more, and gravity squeezes matter until pressure becomes its own kind of warmth. The accepted fact is that early Earth heats substantially during accretion and differentiation, and that as temperatures rise high enough for partial or extensive melting, dense metallic iron separates from silicate rock and sinks to form a core, while lighter silicates remain above as mantle and crust. This differentiation is supported by multiple lines of evidence, including Earth's bulk density, seismic wave behavior revealing a metallic core, and geochemical signatures showing that many siderophile elements preferentially partition into metal, while lithophile elements remain in silicates. Only took a planet gaining enough mass for gravity to insist on layers. The narrative lingers on molten motion, because molten motion is where atoms stop behaving like fixed positions and start behaving like preferences. In a hot, partially molten Earth, iron and nickel do not merely exist as elements. They exist as atoms seeking lower gravitational potential and as chemical species with affinities for metal phases. When metal segregates, it can form droplets that percolate through silicate melt, coalescing into larger streams descending toward the center. This is accepted in principle. Metal-silicate separation occurs when melt fractions are high enough and when pathways allow movement. The descent is driven by density contrasts, but it is regulated by viscosity, melt connectivity, and the physics of emulsions in a convecting mantle. A gentle modern analogy can hover restrained like denser syrup sinking through a thinner fluid. Metal tends to sink through silicate when melting, allows it though the planet's interior is far more complex than any jar. Only took density doing what density does for the Earth to begin becoming internally organized. Yet even as the broad picture is accepted, the narrative holds a quiet scientific mystery that persists. The exact timeline and style of core formation remain uncertain. How quickly does most metal reach the center? Within tens of millions of years in multiple pulses, or in prolonged episodes tied to giant impacts? How much of Earth melts into a global magma ocean, and how deep? How efficiently does metal equilibrate chemically with silicates during descent, and at what pressures and temperatures? These details matter because they influence the mantle's oxidation state, the distribution of volatile elements, and the signatures preserved in isotopes such as hafnium-tungsten that are used to date differentiation. The evidence strongly suggests early core formation, but the choreography, continuous settling versus episodic segregation, remains an active research field. Only took Earth's earliest surface being overwritten to make the core's birth partly inferential. The narrative stays grounded in what can be said with confidence. Seismology reveals that Earth has a liquid outer core and a solid inner core, and that the core is mostly iron with some lighter elements. This is accepted seismic wave speeds and behavior require a dense metallic core with liquid and solid regions. But which light elements are present, sulfur, silicon, oxygen, carbon, hydrogen, or combinations, and in what proportions remains uncertain because direct sampling is impossible, and models rely on high-pressure experiments, ab initio calculations, and constraints from meteorite compositions. This uncertainty is quiet and real. The core's exact recipe is still being refined. Only took the deepest part of the planet being unreachable to keep its ingredients slightly ambiguous. The narrative lets atomic behavior remain central by focusing on partitioning because core formation is chemistry under extreme conditions. In metal silicate separation elements, with affinity for metal hydrophile elements like gold, platinum, and many others tend to follow iron into the core, while lithophile elements like silicon and aluminum prefer silicates, and chalcophile elements have affinities for sulfur phases. This is accepted geochemistry. Yet Earth's mantle contains more of some highly hydrophile elements than simple equilibrium models would predict if all metal sank perfectly, suggesting additional complexity, such as late veneer additions after core formation, incomplete equilibration, or different partitioning behavior at very high pressures. The narrative does not over-explain, it holds the implication as an uncertainty that remains. How precisely do mantle abundances reflect the sequence of core formation, late accretion, and deep chemistry? Only took a trace element in parts per billion to complicate the story of a whole core. A lesser-known real-world detail rests in the possibility of iron snow in certain planetary cores, a phenomenon discussed especially for some terrestrial planets and moons, under particular pressure-temperature conditions. Iron can crystallize near the top of a core and sink as solid particles, while in other cases crystallization begins deeper and grows outward. For Earth, the accepted view is that the inner core grows from the center as the planet cools, but the broader concept is a reminder that core crystallization pathways can vary. Even on Earth, the exact dynamics at the inner core boundary, how crystals nucleate, align, and affect anisotropy remain topics of study. Only took iron deciding where to freeze to influence a planet's magnetic behavior. The ironies arrive softly dry and sleepy without breaking the meditative tone. The first irony is that Earth's deepest structure, core and mantle forms because matter is willing to melt meaning. The planet becomes organized by temporarily losing solidity. The second irony is that the core's formation is one of the most decisive events in Earth history, and yet it happens out of sight, leaving evidence only as indirect signals in isotopes and seismic waves. The third irony is that heavy elements like iron can make a planet more stable in shape and gravity, while their separation also creates the conditions for a magnetic field that later protects the surface from solar wind stripping, so heaviness becomes a kind of quiet shield. Only took weight sinking to become protection later. The narrative lingers on the magnetic field because it is a later consequence of early differentiation. The accepted fact is that Earth's magnetic field is generated by a dynamo motion of electrically conducting fluid in the outer core. Influenced by Earth's rotation, sustains a magnetic field through electromagnetic induction. This requires energy to drive convection in the core supplied by cooling compositional buoyancy, as the inner core solidifies and expels light elements and possibly radiogenic heating from elements like potassium if present in the core in small amounts. Yet the history of the dynamo, when it begins, how strong it is through time, remains an area of research constrained by paleomagnetism in ancient rocks and minerals. Some evidence suggests an early magnetic field, but the record is difficult and debated for the oldest times. Only took magnetized grains in ancient rocks to hint at an invisible shield that may have flickered long ago. The narrative returns again to the molten Earth because core formation does not occur in isolation from surface conditions. Large impacts during accretion can create or refresh magma oceans, temporarily melting large fractions of the mantle and allowing metal to sink more efficiently. In such scenarios, the surface is not stable rock, but a glowing silicate sea, radiating heat to space while volatile gases form a transient atmosphere above it. This is consistent with many models of early Earth and with the energetic nature of planetary accretion. The quiet uncertainty remains. How often does Earth return to a magma ocean state? How quickly does it cool between such events, and how does this affect volatile retention, especially water and carbon? Only took one giant impact to turn a crust back into melt and rewrite the chemical ledger. A subtle, lesser-known detail rests in the role of oxygen fugacity, the effective availability of oxygen for chemical reactions in determining how elements partition during differentiation. Under more reducing conditions, some elements behave more siderophile and move into metal. Under more oxidizing conditions, they remain in silicates. Earth's mantle oxidation state likely changes through time, influenced by accretion of material with different redox states, by metal-silicate equilibration at varying pressures, and by later processes. The accepted fact is that redox conditions matter strongly for partitioning. The uncertainty is the precise evolution of Earth's redox state during and after core formation. Only took how oxidizing the melt is to change where important elements decide to live. The narrative slows into the physical sensation of pressure, because pressure is one of the atom's most revealing teachers. Under extreme pressures, electron orbitals are compressed and mineral structures shift. In metals, electronic properties can change. In silicates, coordination numbers increase. Deep inside Earth, silicon can be coordinated by more oxygen atoms than at the surface, creating denser structures. This is accepted mineral physics. High-pressure phases exist because atomic arrangements adapt under compression. Differentiation is therefore not just gravity sorting, it is also atomic architecture responding to pressure. Only took atoms being flexible under pressure for the mantle to become a different mineral world with depth. The section holds one more quiet mystery close. Because it belongs here, the earliest distribution of volatile elements between core mantle and atmosphere is still not fully resolved. Some light elements may enter the core, some volatiles may be lost during impacts, some may be retained in the mantle and later outgassed. This initial partitioning influences long-term habitability, ocean formation, and atmospheric evolution. Yet because early conditions are hard to reconstruct and because later recycling alters inventories, the uncertainty remains exactly how much of Earth's water and carbon is present from the start, how much is delivered later, and how much is lost or buried deep. Only took the first few tens of millions of years to set constraints that still echo billions of years later. The narrative ends by returning to the calm image of layering, because layering is the planet's first large internal order. A heavy metallic core gathers at the center, liquid and moving. Above it, a silicate mantle convex, slowly cooling. Above that, a crust will eventually form and be broken and remade. All of this depends on atoms behaving in ways that are not simple electrons, shaping bonds, pressure, reshaping orbitals, elements, choosing phases, isotopes, recording time. The young Earth is not yet a place of quiet continents and stable oceans, but it is already a structured body organized by molten sorting and deep chemical preferences, and the unresolved details remain gently, without needing closure, the exact pace of core formation, the core's light element recipe, the early dynamo's history, the earliest redox evolution. In the meantime, the planet continues to cool and its layered interior becomes the hidden engine that will later support every surface scene. Oceans, atmospheres, life built from atoms that were never truly simple to begin with. Cooling continues, and with cooling comes repetition, because the first enduring order on a young planet is not a coastline or a forest, but a lattice. the world begins to trade fluid uncertainty for solid pattern. The accepted fact is that as molten silicate cools, minerals crystallize when temperature, pressure, and composition cross stability boundaries, and those minerals adopt specific crystal structures, regular repeating arrangements of atoms because quantum bonding and electrostatic balance favor certain geometries over others. In other words, the earliest rocks are not merely frozen melt, they are negotiated compromises between atoms, energy, and space written into symmetry and repetition. Only took heat leaving for atoms to decide they prefer places. The narrative remains whisper soft and stays close to a cooling surface that is still young enough to be reset by impacts, yet old enough to begin making crystals that can persist. In a magma ocean or in thick melt sheets, convection stirs, bringing hot material upward and cooler material downward, and within that moving heat nucleation begins. A crystal does not appear everywhere at once. It begins at a point a seed, then grows outward as atoms and ions attach in a pattern that matches the lattice. This is accepted crystallization physics. Nucleation is a barrier-crossing event that depends on undercooling impurities and surface energies, and growth depends on diffusion and attachment kinetics. A lesser-known real-world detail rests in how crystals can grow, with faces that reflect their internal symmetry, creating planar surfaces at angles set by the lattice itself, as if the interior's invisible order chooses how the exterior meets light. Even in volcanic settings, tiny phenocrysts can show sharp faces, and in cavities, crystals can grow freely into open space, making geometry that looks deliberate while being only physics. Only took atoms repeating a spacing to create a flat plane that catches a glint. The narrative lingers on the mineral palette that early Earth likely repeats olivine and pyroxenes in mafic melts, feldspars in more evolved compositions, and the common silica frameworks that later become abundant. The accepted process is fractional crystallization. As certain minerals crystallize, first they remove specific elements from the melt, changing the remaining melt's composition, which then favors different minerals later. This is a cornerstone of igneous petrology, and explains how basaltic parents can, through differentiation, produce more silica-rich magmas in certain contexts. The planet's crustal diversity begins here in a quiet sequence of preferences. Only took a melt crystallizing the easy minerals first for the leftovers to become something new. The narrative keeps imagery elemental, a glowing surface dimming toward the dull red, then black. Beneath melt still moves, and within it crystals rain and float depending on density. Some crystals can settle, some can be buoyant relative to the melt. This is accepted in principle. Crystal settling and flotation can contribute to differentiation, though the efficiency depends on viscosity, convection, and crystal size. A poetic detail emerges in the idea of a crystal mush, a zone where melt and crystals coexist like a slutty interior, not fully liquid, not fully solid, slowly reorganizing as heat leaves. In such mushes, channels can form, melt can migrate, and crystals can compact, all of it quiet and slow like a city forming from repeated bricks without a plan. Only took a partially frozen melt to become a porous breathing stone. The section's quiet scientific mystery settles into focus without raising the voice, even with well-understood thermodynamics. The earliest history of Earth's first long-lived crust remains difficult to reconstruct, and one reason is that crystallization and remelting happen repeatedly, erasing many primary textures. How quickly does the first stable continental-like crust appear, and by what dominant mechanism direct crystallization of differentiated melts, repeated remelting of basaltic crust, or other pathways influenced by water and tectonic style? The existence of very old minerals suggests early crustal components, yet the processes that generate and preserve them remain partly unresolved because the Hadean record is sparse and altered. only took the planet recycling itself to keep its first crust mostly out of reach. The narrative remains grounded and ties crystallization to what can survive mineral stability. Some minerals resist chemical attack and physical breakdown better than others. Zircon in particular is durable, and it can survive multiple cycles of erosion and metamorphism. It is not introduced here as a clock again, but as a crystal whose structure is unusually stubborn, allowing it to carry chemistry and time through chaos. A lesser-known detail rests in how zircon can contain tiny inclusions, microscopic trapped pockets of melt or mineral that preserve a hint of the environment in which the zircon grows. These inclusions can in rare cases suggest the presence of water-rich conditions or particular melt compositions, offering faint clues about early crust and surface environments. Only took a crystal trapping a speck to preserve a whisper of an ancient melt. The ironies arrive softly dry and sleepy, and they drift through the solidifying world without changing its calm. The first irony is that the planet's earliest order is born from disorder. Cooling chaos crystallizes into symmetry as if the world learned structure by losing energy. The second irony is that crystals appear permanent, yet they are conditional. Change the pressure and temperature, and the same atoms rearrange into a different phase, quietly rewriting solidity from the inside. The third irony is that humans call crystals perfect, but real crystals are full of defects, vacancies, substitutions, dislocations, and those imperfections are often what give minerals their colors, strengths, and histories. Only took a missing atom in a lattice to change a gemstone's entire mood. The narrative lingers on phase changes because they reveal atoms as adaptable. Under increasing pressure with depth mineral structures, shift coordination numbers increase, lattices become denser, and entirely new structures become stable. This is accepted mineral physics and is why the mantle is layered not just by chemistry but by phase boundaries that reflect changing atomic packing. The surface mineral world is therefore not the whole mineral world. Deep Earth hosts structures that are stable only because pressure forces atoms closer and reshapes electron distributions. A gentle modern analogy can hover restrained, like a crowd compressing through a narrow doorway, forces people to stand differently. Pressure forces atoms into tighter arrangements, though the analogy remains soft because atoms do not choose, they obey. Only took pressure, being relentless, for the same chemistry to become a different structure. The narrative now introduces the section's deeper, quieter philosophical uncertainty in a way that does not repeat earlier. Explanations only touches them as a soft callback. Crystals exist because atoms are stable, and atoms are stable because the universe's constants and quantum rules permit bound states with long lifetimes. That permission is measurable spectral lines, bond energies, nucleus stability, and it is taken as given in physics, yet the deeper reason the constants have these values remains unresolved in fundamental terms. This is not presented as a drama, it is presented as a calm horizon. If constants were significantly different, stable atoms and long-lived crystals might not exist, and Earth's entire slow history of rock and water would be impossible. Only took the rules being this way for stone to be a long-lived thing. The narrative returns quickly to Earth because Earth is the place where this abstract permission becomes tangible. A cooling basalt forms interlocking crystals, and those crystals control how the rock fractures and weathers. Feldspars can break down into clays, releasing ions to water. Quartz can persist longer, accumulating as sand. These are accepted weathering tendencies. Mineral stability at Earth's surface follows patterns tied to formation conditions and chemical resilience. The first crystals therefore begin not only geology, but the chemistry of landscapes, because once water exists, mineral dissolution and precipitation become continuous processes. The section does not rush into oceans yet, it simply notices that crystallization creates surfaces and surfaces create reactions. Only took a crystal face meeting water for the slow exchange between rock and liquid to begin. A lesser-known detail rests in the way some crystals reveal their growth in microscopic patterns zoning, twinning, exsolution, lamellae, where a mineral unmixes into two phases as it cools. In feldspars, for instance, exsolution can produce fine intergrowths that record cooling histories, and in some minerals twinning creates repeated mirror-like domains, as if the lattice rehearses symmetry with a slight hesitation. These features are real and diagnostic, used by petrologists to infer thermal and chemical evolution. Only took a crystal cooling slowly enough for it to separate into stripes within itself. The narrative stays slow and returns to the broader transformation. Crystallization is the moment Earth becomes a world of persistent solids, rather than a temporary melt. Yet persistence is not permanence. Impacts can remelt, tectonics can recycle metamorphism, can reorganize lattices. Crystals endure by being stable within ranges, and they change when conditions shift. This conditional endurance becomes Earth's long rhythm build, alter-rebuild. It is a rhythm written in atoms that prefer certain distances, certain angles, certain electron arrangements. And within that rhythm, the planet begins to develop a kind of memory, not a conscious memory, but a structural one where the past remains embedded in textures, inclusions, defects, and phase assemblages. Only took atoms repeating themselves to make stone remember. The section ends in a quiet close-up, a single crystal growing in a cooling melt layer by layer, each layer a repetition that looks smooth from afar and granular up close. Around it, other crystals grow interlock, and together they become rock. Above, heat radiates into space. Below, pressure increases with depth reshaping structures. The world becomes more solid, and yet it remains dynamic because the same atomic rules that build lattices also allow transformation when energy and pressure demand it. The mystery remains softly open. The exact pathway to Earth's first durable crust is still partly hidden, and the deeper reason the constants allow stable atoms at all remains beyond complete explanation. Still, crystals form quietly, and in their forming the planet takes its first long step toward being a place where time can leave marks that last. Cooling continues, and now the solid lattice meets its most patient sculptor, because when water arrives it does not merely sit on rock, it begins to negotiate with it atom by atom, dissolving, carrying, depositing and rewriting surfaces without urgency. The accepted fact is that Earth's oceans form as the planet cools and water vapor condenses, with much of the water supplied by degassing of Earth's interior volatiles released from magma, while additional contributions may come from water-bearing planetesimals. Once liquid water exists, chemical weathering and dissolution begin transferring ions from rock into seawater, establishing the ocean's salinity and driving long-term geochemical cycles. This is not a single instant, but a long settling into stability. Steam becomes rain, rain becomes runoff, runoff becomes river, and river becomes the slow delivery system for dissolved atoms. Only took a planet radiating heat to space for steam to become the first rain, and then the rain begins the world's quiet chemistry. The narrative stays whisper soft and lingers on the first contact water, touching fresh basalt, seeping into fractures, reacting with minerals whose atoms are arranged in careful lattices, but whose surfaces are chemically eager. Hydrogen ions and water molecules interact with mineral bonds, breaking some, forming others, pulling ions into solution. In basalt, calcium, magnesium, sodium and silica can be mobilized. In early crustal materials, iron can also enter solution in reduced form, depending on oxygen availability. This is accepted geochemistry. Silicate weathering consumes carbon dioxide when carbonic acid forms in water, producing bicarbonate and dissolved cations that are transported to the ocean, where carbonates can precipitate under suitable conditions. The narrative does not overstate. It simply holds the principle that water is not neutral because water is a solvent and a reactant. A lesser-known real-world detail rests in how even pure rain is naturally slightly acidic because it equilibrates with atmospheric carbon dioxide to form carbonic acid. And this mild acidity is enough given time to dissolve minerals and carry their atoms away. It is a gentle chemical insistence like a soft file that never stops. Only took a thin film of weak acid to wear down mountains eventually, without needing force. The ocean begins to taste of rock because ions accumulate, and salinity becomes a physical property of the sea rather than a metaphor. Sodium and chloride become dominant in modern oceans, but their relative abundances emerge from sources and sinks river input, hydrothermal exchange at mid-ocean ridges, evaporite formation, biological uptake and sediment burial. The accepted fact is that seawater composition is shaped by balance between inputs and removal processes, with hydrothermal circulation playing a major role by exchanging ions between seawater and hot basaltic crust, removing magnesium, for example, and adding calcium and other species under certain conditions. Yet the section's quiet scientific mystery remains: what exactly is the composition of the earliest oceans, and how quickly does salinity rise to something comparable to today? The rock record does not preserve a bottled sample of Hadean seawater, and proxies for ancient salinity and ionic ratios are indirect and often contested. Models can explore plausible ranges, but precise values remain uncertain. Only took billions of years of circulation for the original recipe to become impossible to taste directly. The narrative stays grounded by turning to hydrothermal systems because they are among the most direct ways atoms travel between rock and water. Seawater percolates into oceanic crust at ridges, and fractures heats, reacts with minerals and returns to the ocean altered, carrying dissolved metals and changing the ocean's chemistry. This is accepted. Hydrothermal vents exist today, and have likely existed since early oceans given a hot interior and active volcanism. In these systems, water becomes a moving chemical interface between the mantle's heat and the ocean's mass. A poetic detail appears in the mineral chimneys that form where hot fluids meet cold seawater, precipitating sulfides and carbonates in layered porous towers, stone growing out of water, as if the ocean briefly remembers how to build upward. Only took hot water meeting cold water for minerals to decide they prefer to be solid again. The narrative keeps atoms as the central characters without personifying them. Ions move because gradients exist, because diffusion and advection transport dissolved species, because charge balance is maintained, because water molecules orient around ions, forming hydration shells that stabilize them in solution. The accepted fact is that ions in water are surrounded by structured shells of water molecules, and these hydration shells affect mobility and reactivity. Sodium and chloride remain highly soluble, largely because their hydrated forms are stable, while other ions can precipitate readily when conditions shift. A gentle modern analogy can hover restrained, like passengers surrounded by personal space in a crowded station. Ions carry hydration shells that shape how they move and interact. Though the analogy stays soft because molecules do not choose, they follow energetics. Only took water molecules aligning around charge to make the ocean a mobile reservoir of dissolved rock. The ironies arrive softly, 3 dry observations that do not disturb the calm. The first irony is that the ocean, often imagined as pure, is in fact a diluted rock solution, and its saltiness is Earth's crust becoming partially dispersed. The second irony is that water's softness is what makes it powerful. It breaks stone not by strength, but by persistence and chemistry. The third irony is that humans call land solid ground, yet the ground's atoms are constantly leaving in solution, and returning as precipitates elsewhere, as if solidity is only a temporary arrangement. Only took a few ions escaping per second for continents to be slowly exported to the sea. The narrative lingers on rivers as conveyors because rivers are the planet's long-distance transport for ions. Weathering releases calcium, sodium, potassium, magnesium, silica, bicarbonate, and a host of trace elements. Rivers carry them to the ocean. In the ocean, some remain dissolved for long residence times. Some are taken up by organisms, some precipitate as minerals, some adsorb onto particles and sink. The accepted fact is that different ions have different residence times. In seawater, chloride and sodium are long-lived, while iron is short-lived in oxygenated modern seawater because it precipitates and is scavenged. Yet early oceans with different redox states likely hold iron differently, and the precise speciation and concentrations remain uncertain. The quiet mystery persists. How does early ocean redox and pH shape which ions travel far and which settle quickly? And how does this influence the formation of early sedimentary rocks and the availability of nutrients for life? Only took oxygen being scarce for iron to remain mobile, and the sea to be chemically unfamiliar. A lesser-known detail rests in the way silica behaves. Modern oceans are far from saturated with respect to quartz, but can be influenced by biological uptake of silica by organisms like diatoms which do not exist in the earliest oceans. In early Earth settings, silica concentrations may be higher, and silica can precipitate in hydrothermal and sedimentary contexts, contributing to chert formation. The timing and mechanisms of widespread chert deposition and the interplay between hydrothermal input and ocean chemistry remain topics of research. Chert, when seen in ancient sequences, becomes a quiet mineral memory of silica moving through water long before silica skeletons dominate. Only took dissolved silica finding a reason to solidify for the seafloor to gain glassy layers. The narrative stays slow and notices that water also changes the rocks it enters. Basalt altered by seawater can form clay zeolites and hydrated minerals. Serpentinization, a process where ultramafic rocks react with water, produces serpentine minerals and can generate hydrogen gas. This is accepted geochemistry. Serpentinization is not only alteration, it is an engine for chemical energy producing reduced compounds that can feed microbial metabolisms and influence ocean chemistry. The quiet scientific uncertainty here is not whether serpentinization occurs, it does, but how widespread and influential it is on early Earth, and how it contributes to the availability of chemical energy at the origin of life and beyond. Only took water entering the right kind of rock for hydrogen to appear as a byproduct quietly like a new currency. The narrative keeps the ocean's formation within a wider planetary context. The young sun is fainter than today, and yet geological evidence indicates liquid water exists. Early, a tension often called the faint young sun paradox. The accepted fact is that the sun's luminosity increases over time, and that early Earth receives less solar energy, raising questions about how oceans remain unfrozen. Proposed solutions involve higher greenhouse gas concentrations, different cloud properties and other feedbacks, but the exact balance remains debated. This becomes the section's deeper calm mystery. In the background, water exists, but the precise climatic conditions that allow stable liquid water under a dimmer sun are still being refined. Only took the sun being younger for Earth's early warmth to become a long-standing puzzle. The narrative holds this without urgency and returns to the chemistry of carbon dioxide because it links water, rock and climate. Carbon dioxide dissolves in water forms, carbonic acid reacts with silicate minerals, and ultimately can be stored as carbonate minerals, a long-term, stabilizing feedback in Earth's climate system. This is accepted in broad outline. The carbonate-silicate cycle regulates CO2 over geological timescales, yet the early efficiency of this cycle depends on continental area erosion rates, ocean chemistry and tectonic style, all of which are uncertain in the earliest eons. Only took a feedback requiring continents to exist for early climate regulation to be partly unknowable. A poetic detail appears in the fact that the ocean's saltiness and its buffering capacity are in a way the planet learning to hold itself steady ions in solution, moderate pH changes, carbonate, chemistry absorbs shocks, and the sea becomes a stabilizing reservoir as much as a moving one. But stabilization is never complete. The ocean remains dynamic, exchanging with rock at ridges, receiving rivers evaporating and raining back. It is a continuous conversation between lattice and solvent. The narrative ends by returning to the close-up of atoms travelling a calcium ion, freed from a feldspar lattice in a weathering rock captured by water molecules carried by a stream joining a river entering the sea, circulating for years or millennia, perhaps precipitating as carbonate in a shallow shelf, perhaps being subducted later in altered oceanic crust, perhaps released again through volcanism. This loop is accepted in principle as part of Earth's geochemical cycling, even though the earliest loop's exact parameters remain uncertain. The ocean is therefore not only a surface feature, it is a vast transport network for atoms, a place where tiny worlds become mobile, where lattices dissolve into travellers, and where the planet's long history is written, not only in stone but in the slow motion of ions through water. The ocean now holds dissolved atoms like quiet passengers, and the narrative turns to the messenger that reads them without touching them, because light is the gentlest probe the universe offers. It arrives, it leaves, and in leaving it carries signatures that are not invented, only obeyed. The accepted fact is that atoms and molecules absorb and emit light at specific wavelengths because their electrons and vibrational rotational states occupy quantized energy levels. When transitions occur between these levels, photons of particular energies are involved, creating spectral lines that function as fingerprints. This is why astronomers can determine the composition of distant stars, and why chemists can identify substances in a laboratory. Only took electrons stepping between allowed energies for the universe to become readable at a distance. The narrative remains whisper-soft and returns to Earth's early sky as a thin layer of gas under a young sun, because it is here that spectra are not just a tool of observation, they are also a physical influence. Sunlight arrives in a range of wavelengths, including ultraviolet, visible and infrared, and Earth's atmosphere and surface selectively absorb and scatter parts of that light. The accepted process is radiative transfer. Photons interact with molecules through absorption and scattering, and those interactions shape temperature and chemistry. But even before the atmosphere is oxygen-rich gases, like carbon dioxide, water vapor, methane, and others can absorb infrared, contributing to greenhouse warming. The planet's early climate therefore depends not only on how much light arrives, but on how atomic and molecular transitions in the atmosphere decide which light is trapped and which escapes. Only took a few molecular bands in the infrared for oceans to remain liquid under a fainter sun. A lesser-known real-world detail rests in the fact that spectral lines in real gases are broadened and shifted by pressure and temperature. Collisions between molecules broaden lines, and motion causes Doppler broadening, meaning that the same molecule can absorb across a range rather than at a single razor-thin frequency. In dense atmospheres, this can significantly change radiative behavior. This is accepted spectroscopy. It means that the atmosphere's ability to trap heat is not only about composition, but also about pressure and structure. Only took molecules bumping into each other to thicken the atmosphere's fingerprints. The narrative stays calm and lets light become a bridge between the tiny and the vast. A photon's energy matches a gap between quantum states. When it does, it can be absorbed. This simple matching rule, repeated billions of times, shapes everything from the color of a flame to the temperature of a planet. Yet the section holds a quiet scientific mystery that feels philosophical while staying real. Why does mathematics describe spectral behavior so well? The Schrödinger equation, quantum electrodynamics, and molecular spectroscopy produce predictions that match measurements to astonishing precision. This is accepted as a triumph of physics, and yet the deeper reason the universe is so mathematically structured remains open to interpretation. Only took a line on a graph matching a line in a spectrum to make nature feel uncannily legible. The narrative returns to Earth's rocks to keep the grounding firm. Minerals reflect and absorb light in ways that depend on electron structures and impurities. Iron in different oxidation states can produce different colors. Trace elements can create color centers. Lattice defects can alter absorption. This is accepted solid-state physics and mineralogy. A poetic detail appears in the way a mineral can carry color as a record of its atomic environment. Amethyst owes its purple to iron and irradiation-induced defects. Smoky quartz darkens through radiation damage. Some feldspars shimmer through exsolution lamellae. These are real phenomena. Only took a few defects in a lattice for a stone to carry a hue like a quiet memory of radiation and chemistry. The narrative now shifts gently to how humans learn to read these signatures. Spectroscopy in earth science includes techniques like infrared absorption, Raman scattering, X-ray fluorescence, and mass spectrometry. Each relies on quantized interactions between energy and matter. The accepted fact is that these tools allow identification of elements and compounds sometimes at trace levels. In deep time work they can detect isotopic ratios and mineral phases that reveal conditions of formation. Yet the quiet uncertainty remains. Ancient signals are often altered by later processes, and interpretation requires care. Only took a precise measurement to still need context to mean anything. The ironies arrive softly dry and sleepy without any shift in tone. The first irony is that light which feels intangible becomes one of the most reliable ways to know the composition of distant and ancient things. The second irony is that human eyes perceive only a narrow band of the electromagnetic spectrum, while most of the planet's crucial energy exchange happens in infrared wavelengths that are invisible without instruments. The third irony is that the universe offers these precise spectral fingerprints freely, yet it still hides some of its deepest answers, like why constants have their values behind the very success of the fingerprints. Only took clarity at one level to leave mystery at another. The narrative keeps the focus on Earth's early atmosphere again, because in an oxygen-poor sky, ultraviolet light behaves differently. Without a strong ozone layer, more UV reaches the lower atmosphere and surface-driving photochemistry that can produce hazes or alter greenhouse gas lifetimes. Methane can be more stable and organic aerosols can form under certain compositions affecting albedo and climate. These are accepted possibilities supported by the models and analogues like Titan, though the exact composition and haze extent on early Earth remain uncertain. The quiet scientific mystery here is how much haze exists, how it affects climate, and how it interacts with greenhouse warming under the faint young sun. A haze can cool by reflecting sunlight, yet it can also warm depending on the particle properties and infrared absorption. Only took tiny particles suspended in air to make early climate sensitive in multiple directions. A gentle modern analogy can hover restrained like frosted glass that both blocks light and holds warmth behind it. Atmospheric aerosols can reduce incoming sunlight, while altering outgoing heat, though the analogy remains soft because real radiative effects depend on wavelength, particle size, and composition. The narrative continues to link light to chemistry. Photodissociation breaks molecules when photons carry enough energy to break bonds. Ultraviolet light can split water vapor high in the atmosphere, producing hydrogen that can escape to space and oxygen that can react with other gases or be lost to sinks. Hydrogen escape is an accepted process that can over long time influence a planet's oxidation state. The exact role of hydrogen in escape in Earth's early redox evolution is debated, but it is a credible factor. The quiet mystery becomes how strongly does light-driven escape alter Earth's long-term atmosphere, and how does this interplay with geology and biology? Only took the lightest atom escaping to space to change a planet's chemistry slowly. The narrative stays slow and returns to the ocean's dissolved atoms because spectra do not only read atmospheres, they also read water. Water absorbs strongly in infrared. Dissolved ions can influence optical properties. Suspended particles scatter light. But more importantly, light at the surface powers photosynthesis. And photosynthesis is itself an atomic process. Photons excite electrons in pigments, initiating electron transfer chains. The accepted fact is that photosynthesis begins with light absorption by pigments and subsequent charge separation, a quantum influence process that can be described with both classical and quantum models. Yet the origin of photosynthesis and why certain pigments evolve remains partly uncertain in the deep record. Only took a photon being captured to begin a biological pathway that later alters the entire atmosphere. The narrative maintains continuity by recalling earlier motifs without repetition. Atoms are not simple beads, they are quantized systems. Now those quantized systems interact with light, and that interaction scales to climates and to life. The planet's earliest oceans exist under a sun that is fainter than today, and the atmosphere's greenhouse capacity depends on spectral absorption. This is accepted. Yet the faint young sun paradox remains unresolved in full detail. Different combinations of greenhouse gases, cloud surface albedo, and atmospheric pressure are proposed, and the evidence is indirect. The narrative lets this uncertainty remain as a calm gap, because the gap is honest. Only took one paradox to keep early Earth climate as a continuing research frontier. A lesser-known detail rests in how scientists can infer ancient atmospheric pressure using proxies such as fossil raindrop imprints or nitrogen isotopes and basalt vesicle sizes, though these methods carry uncertainties and debates. The idea is that pressure affects bubble sizes and raindrop terminal velocities, leaving potential records, but preservation and interpretation are challenging. Still, it is a real attempt to read the weight of ancient air from subtle traces. Only took a bubble trapped in cooling lava to hint at how heavy the sky once is. The narrative closes the section with light leaving Earth at night as infrared radiation carrying the planet's temperature field outward into space. This emission is not a metaphor. It is the planet's steady accounting of energy. The same quantum rules that shape spectral lines shape the greenhouse effect, and the greenhouse effect shapes whether oceans remain liquid, whether weathering continues, whether life's chemistry can persist. Atoms, light, and climate are therefore one continuous system bound by quantized transitions and by the slow flow of heat. The world is readable because it emits and absorbs in patterned ways, and yet the reason it is so readable remains quietly mysterious. In the meantime, photons continue to arrive and atoms continue to respond, and Earth continues to be built and warmed and altered by the simplest seeming interaction that is never truly simple light meeting matter. Heat continues to leave the young planet, light continues to arrive and depart, and within the cooling stone another kind of motion continues, even when nothing seems to move at all, the quiet rearrangement of nuclei. The accepted fact is that some atomic nuclei are unstable and undergo radioactive decay, transforming into other nuclei at predictable average rates characterized by half-lives, and this statistical predictability allows radiometric dating of rocks and minerals across Earth history. Uranium decays to lead through long chains, potassium decays to argon rubidium, decays to strontium samarium to neodymium, and many other systems exist, each with its own clockwork pace. only took matter being slightly too energetic in its nucleus for timekeeping to be built into stone. The narrative remains whisper-soft and stays close to a single crystal that forms in cooling rock because in that crystal, the atom's complexity becomes a calendar. When a zircon grows, it readily incorporates uranium atoms into its lattice because uranium can substitute into the crystal structure under certain conditions while it tends to exclude lead at formation, meaning that any lead found later is largely radiogenic produced by decay. This is accepted geochronology in broad principle, and it is why zircons are valued as time capsules. The story does not repeat earlier discussion of zircons as a main theme. It uses the crystal simply as a quiet stage where nuclei do their slow work. Only took a lattice preferring uranium over lead for a mineral to become a clock by accident. The narrative lingers on what decay means physically. In alpha, decay, a nucleus emits an alpha particle, a helium nucleus, losing 2 protons and 2 neutrons and becoming a different element. In beta decay, a neutron can transform into a proton with the emission of an electron and an antineutrino, or a proton can transform into a neutron with a positron and a neutrino depending on the decay mode, shifting the element's identity by 1. These are accepted nuclear processes governed by the strong and weak interactions. In each case, the parent nucleus changes to a daughter nucleus, and the change releases energy. That energy can appear as kinetic energy of emitted particles and as gamma rays. The planet's rocks are therefore not perfectly inert. Some contain nuclei that gently release energy as they transform. Only took a few atoms per trillion decaying to contribute heat to an entire mantle over billions of years. A poetic detail rests in the concept of helium as a subtle byproduct of Earth's deep time. Helium atoms produced by alpha decay can become trapped in mineral lattices, can accumulate in pore spaces, can migrate through rock, and in some places can emerge as part of natural gas reservoirs. Some helium used in laboratories and hospitals is in a sense the aged breath of uranium and thorium decay gathered from ancient crustal sources. Only took a nucleus shedding an alpha particle for a balloon's lift to be connected to deep geology. The narrative keeps the tone even and lets this be a calm observation rather than a flourish. The accepted process at the center remains radiometric dating. Because decay rates are statistically constant under ordinary Earth conditions, the ratio of parent to daughter isotopes in a closed system changes predictably with time, and by measuring those ratios and applying known decay constants, ages can be calculated. This is the basis for dating the age of Earth materials and for constructing the timeline of planetary evolution. Multiple independent dating systems often converge on consistent ages when samples are well-behaved, reinforcing confidence. Only took nuclei ignoring pressure and temperature changes in most circumstances for time to be readable in the crust. Yet the narrative holds a quiet scientific mystery exactly where it belongs. Why is radioactive decay fundamentally probabilistic? Quantum theory can calculate decay rates using tunneling and interaction probabilities, and those rates match observations, but it does not provide a deterministic schedule for when any specific nucleus will decay. One uranium atom may decay now, another identical uranium atom may persist for 1 billion years longer. The average behavior is law-like, the individual event is not predictable in the same way. This is not a gap in measurement technique, it is an intrinsic feature of the current theory. The deeper meaning of that randomness remains a point of interpretation in physics. Only took the best clock humans have being built from events that cannot be individually foretold. The narrative stays grounded by returning to how this probabilistic behavior produces reliable time anyway. In a mineral containing trillions of atoms, the law of large numbers makes the overall decay behavior extremely stable. The fraction that decays per unit time becomes predictable, and the parent-daughter ratios become robust clocks. It is the same quiet paradox seen elsewhere, large-scale certainty emerging from small-scale unpredictability. Only took enough atoms acting together for randomness to become reliable. A gentle modern analogy can hover restrained like a vast crowd where no one can predict which person will leave the stadium next yet. The flow rate through the exits becomes steady and measurable. Decay in large populations becomes smooth. The analogy remains soft and does not overreach. The ironies arrive softly dry and sleepy, 3 of them without shifting tone. The first irony is that time which feels abstract is measured most confidently by counting tiny nuclear transformations that no one can watch directly. The second irony is that the very instability of some atoms is what grants stability to the geological timeline, as if uncertainty is the foundation of certainty. The third irony is that the same decay that lets rocks be dated also slowly damages the crystals that hold the record, because emitted particles can disrupt lattices and create defects. Only took a clock that gently scratches its own face while it runs. The narrative lingers on that last point because it is a real lesser-known detail. Radiation damage can accumulate in minerals producing metamic textures, where the crystal structure becomes partially amorphous. In zircon and other minerals, this damage can affect diffusion pathways and influence how well the system remains closed. In some contexts, lead can be lost from damaged domains, and later heating can partially reset or disturb ages. This is accepted in geochronology. Not all mineral grains are perfect recorders, and interpreting ages requires understanding the mineral's history, thermal events, and potential open system behavior. Only took a few nanometers of damage to turn a clean age into a complicated one. The narrative stays calm and notes that the science is built to handle such complications through methods like Concordia diagrams in uranium-lead dating, step heating in argon dating, and cross-checking multiple minerals and isotope systems. These are standard tools, and they reflect the broader truth that Earth is not a laboratory sealed from disturbance. Time is read from imperfect archives. Only took the planet being active for every measurement to include a question of closure. The narrative returns to radiogenic heat as a quiet engine of Earth history. Long-lived isotopes of uranium, thorium, and potassium contribute significantly to Earth's internal heat budget, helping sustain mantle convection volcanism and plate tectonics over billions of years. This is accepted geophysics. Without radiogenic heat and primordial heat from formation, Earth would cool more quickly, potentially reducing tectonic activity. The exact proportions of heat sources and the distribution of radioactive elements between crust mantle and core are still refined, and the mantle's composition is not directly sampled everywhere, but the principle stands. Nuclear decay is part of why the planet remains dynamically alive. Only took trace elements in the right places to keep continents moving long after formation. A lesser-known detail rests in the way radioactive isotopes can be concentrated by geological processes. In Earth's crust, incompatible elements, those that prefer melt, tend to concentrate in magmas that rise and evolve, meaning uranium and thorium become enriched in continental crust relative to mantle. This creates a crust that is not only chemically distinct but also more radiogenic per unit mass, contributing to localized heat production that can influence metamorphism and crustal melting. The planet's heat is therefore not uniform, it is patchy, shaped by differentiation and recycling. Only took atoms preferring the melt phase for some regions of crust to be warmer from within. The narrative holds another quiet uncertainty that belongs to this section. The exact timing of some early Earth events depends on interpreting isotope systems under uncertain early conditions. Dating the formation of the Moon, for example, and the timing of core formation often relies on short-lived isotope systems like hafnium-tungsten, which are sensitive to early differentiation and mixing. These systems are powerful but require assumptions about initial abundances and reservoir behavior. The ages are constrained, yet details remain debated. The story does not pursue the moon. It simply notes that even the best clocks must be read with context, especially in the earliest eras. Only took a clock with a short half-life to make early events feel both constrained and still arguable. The narrative remains centered on the atom as a tiny world not simple. A nucleus is not a static bead. It is a quantum system with forces and energy levels and probabilities. The strong force binds nucleons tightly, yet not always tightly enough for perfect stability. Quantum tunneling allows alpha particles to escape from a nucleus, even when classical energy barriers would forbid it making decay possible across long timescales. This is accepted nuclear physics. Alpha decay involves tunneling through a potential barrier. The idea is gentle and strange. A particle passes through what it cannot climb over, and the rate at which it does so becomes a half-life that can be measured with precision. Only took a particle slipping through a barrier to write the planet's most trusted timestamps. The narrative slows further and returns to Earth's surface sensations as a quiet anchor. A cliff face looks ancient and still. A grain of sand looks ordinary, yet within some grains nuclei decay in silence, turning uranium to lead potassium, to argon rubidium to strontium, each system adding to the planet's internal warmth and to the record of time. The ocean carries ions, but the rocks carry ages. Light reads atoms in spectra, but isotopes read time in ratios. Each reading is an interaction with the same underlying truth matter, is quantized and structured, and its smallest parts carry behaviors that scale into continents and clocks. The central mystery remains softly open and unforced. Why quantum events are probabilistic at the level of individual decay, and whether that randomness reflects a fundamental aspect of reality or a limit of interpretation. The narrative does not resolve it. It simply rests with the steady consequence despite randomness. In each event, the planet's rocks keep time with patience, and the tiny worlds inside atoms prove again that what seems simple at a glance becomes, when listened to closely, a deep and quiet complexity that never stops unfolding. The ocean continues to hold dissolved atoms in slow circulation, and now the narrative follows one of the quietest yet most influential kinds of motion an atom can make: the movement of an electron. The accepted fact is that redox reactions, reduction and oxidation, are fundamentally transfers of electrons that change an element's oxidation state, and these transfers control which minerals are stable, which ions remain dissolved, and which precipitate out of seawater. On early Earth, where free oxygen is scarce in the atmosphere for long spans, redox conditions differ sharply from the modern world, and those differences shape the chemistry of oceans and the types of sediments that accumulate. Only took an electron-shifting ownership for seawater to decide whether iron stays mobile or becomes stone. The narrative remains whisper-soft and holds a simple image: dark water above a young seafloor, hydrothermal fluids rising, minerals growing where hot meets cold, and in the water column dissolved iron, travelling in a form that would be unusual in a modern oxygenated sea. In anoxic or low oxygen conditions, ferrous iron Fe2 is far more soluble than ferric iron Fe3. This is accepted aqueous geochemistry. It means that early oceans can carry significant dissolved iron, especially with continuous hydrothermal supply and limited oxidative removal. When oxidants appear, whether through localized oxygen production by microbes through photochemical oxidants, or later through broader atmospheric oxygenation, iron can oxidize and precipitate as iron oxides or other iron-bearing minerals, removing it from solution. The ocean in this way becomes a giant redox reactor. Only took oxygen appearing in small places for the sea to begin stripping down itself of dissolved iron. A poetic real-world detail lingers in the way iron precipitation can create layered deposits that look almost like quiet rhythm made visible. Banded iron formations with alternating iron-rich and silica-rich layers are among the most evocative records of ancient ocean chemistry. Their broad association with changing redox conditions is accepted, though the precise reasons for the fine banding, seasonal cycles, microbial productivity pulses, ocean mixing patterns, changes in hydrothermal flux or combinations remain debated. The rock looks patterned and the pattern invites interpretation, yet the seafloor that makes it is never a metronome. Only took chemistry happening repeatedly for stone to look like it remembers a beat. The narrative stays calm and introduces the section's quiet scientific mystery without trying to solve it. What exactly controls the timing and spatial patchiness of early oxygen and other oxidants in the Archean Ocean? Evidence suggests that oxygen can exist locally in oases near photosynthetic microbial mats, even when the global atmosphere remains largely anoxic, and that redox conditions can vary strongly by depth and region. But the extent of these oases, the persistence of oxygen in surface waters, and the degree to which the deep ocean remains anoxic at different times are still being refined through proxies such as ion speciation sulfur, isotopes, trace metal patterns, and sedimentology. The ocean is vast and the rock record is fragmentary. The uncertainty is not a failure, it is a boundary of what survives. Only took a layered ocean to make global a difficult word. The narrative moves through a few core redox players, each grounded in accepted chemistry. Iron is one, sulfur is another. In anoxic environments, sulfate may be lower in concentration than today, while sulfide produced by microbial sulfate reduction or hydrothermal input can be significant in certain settings, leading to the formation of iron sulfides like pyrite. Pyrite formation depends on both iron availability and sulfide, and it can sequester sulfur and iron into sediments. This is accepted biogeochemistry. Microbial metabolisms and chemical reactions convert sulfur between oxidation states, and those states control mineral precipitation. A lesser-known detail rests in pyrite's nickname fool's gold, which is a surface-level human irony. But the deeper geochemical detail is that pyrite formation can also preserve isotopic signatures of microbial activity because microbes fractionate sulfur isotopes in characteristic ways under certain conditions. Those fractionations can later be read with care as hints of metabolic processes in ancient environments. Only took microbes preferring lighter isotopes to leave fingerprints in a glittering mineral. The narrative keeps the pacing slow and returns to the idea that redox is not a single switch. It is a gradient that can exist across millimeters and across kilometers. In modern seas, oxygen can be abundant near the surface and absent in sediments. In early seas, the boundary can shift and different oxidants can play roles. Even without oxygen, other electron acceptors exist: nitrate, sulfate, ferric, iron, carbon dioxide, and more. The energetics differ. Microbial communities adapt to whatever redox ladder the environment provides. This is accepted microbial ecology and biogeochemistry. Only took life learning to use different electron acceptors for ecosystems to exist in darkness and without air. The ironies arrive softly dry and sleepy without raising the emotional level. The first irony is that the ocean's most dramatic chemical changes can be driven by invisible electron transfers, while the waves above look the same. The second irony is that oxygen, the gas later associated with life, begins as a local pollutant to many anaerobic microbes, and yet its small presence can reorganize entire mineral cycles. The third irony is that the rocks most used to early ocean chemistry often form because that chemistry removes substances from the ocean, meaning the record is written by what disappears from water into stone. Only took the ocean losing its dissolved iron for humans to later find iron-rich rocks and ask why. The narrative lingers on the chemistry of silica because iron rarely acts alone. Early oceans may carry higher dissolved silica than modern oceans, partly because silica-secreting organisms are absent for much of early time, and because hydrothermal input can be substantial. High silica can influence how iron precipitates and what minerals form, potentially contributing to the alternating iron and silica layers in banded iron formations and related deposits. The accepted part is that silica cycling differs across Earth history. The uncertain part is exactly how silica concentrations vary in Archean oceans, and how that variation couples to iron precipitation mechanisms. Only took one dissolved component being higher to change the texture of an entire sedimentary record. A gentle modern analogy can hover restrained like a solution that crystallizes differently, depending on what else is dissolved. Seawater's recipe determines which solids appear when conditions shift. The analogy stays quiet and limited because the ocean is not a beaker, but it shares the principle that mixtures govern outcomes. The narrative now turns toward a real-world detail that is subtle but important: iron speciation in sediments as a proxy. In many studies, the relative amounts of highly reactive iron forms versus total iron, and the presence of pyrite versus iron oxides are used to infer whether bottom waters are oxygenated, ferruginous iron-rich anoxic, or euxinic sulfide-rich anoxic. This is an accepted proxy framework, though it requires careful calibration and contextual interpretation. It is less poetic and more methodical, yet it is a quiet reminder that Earth history is reconstructed from chemical partitions, atoms sorted into categories by reactivity. Only took an extraction experiment in a lab to help describe an ocean that no one can see. The narrative holds the uncertainty that comes with this. Sediments can be altered after deposition, and local basins do not always represent global conditions. An iron-rich signal in one basin might reflect restricted circulation. A sulfide-rich signal might reflect high organic productivity and sulfate availability locally. The ocean of early Earth is not necessarily uniform, and the rock record samples it unevenly. The quiet mystery persists how to scale local redox reconstructions into a coherent global picture without overstating confidence. Only took one well-preserved basin to tempt a global conclusion. The narrative returns to life's role without dramatizing it. In some places, microbial photosynthesis produces oxygen in surface waters. In others, chemosynthetic communities use redox gradients supplied by hydrothermal fluids. Microbes cycle iron itself. Some oxidize Fu to Th using light or other pathways. Others reduce Fu back to Fe2 using organic matter or hydrogen as electron donors. This is accepted. Microbiology iron metabolism exists today and is plausible in early Earth environments. These microbial processes can influence mineral precipitation and dissolution, creating feedbacks between biology and geology even before oxygen dominates the atmosphere. Only took microbes turning iron into a food source for the seafloor to become a living chemistry. A lesser-known detail rests in a particular pathway often discussed in early Earth contexts. Photoferrotrophy, where microbes use light to oxidize ferrous iron instead of water-producing ferric iron minerals without releasing oxygen. This metabolism exists in some modern oxygenic phototrophs and is studied as a potential contributor to ancient iron deposition. Yet the extent to which photoferrotrophy contributes to banded iron formation deposition versus abiotic oxidation or oxygen-driven oxidation remains debated. The uncertainty is real and quiet. Multiple processes can yield similar mineral outcomes, and distinguishing them in ancient rocks is difficult. Only took different pathways producing similar minerals for interpretation to remain delicate. The narrative keeps the planetary scale present. Redox state is not only an ocean property, It is also a mantle and crust property. The oxidation state of volcanic gases influences atmospheric composition. The burial of organic carbon can leave behind oxygen equivalents in the surface system. Hydrogen escape to space can over long time oxidize the planet by removing reducing power. These are accepted concepts in Earth system science, though their magnitudes and timing through early history remain refined. The quiet mystery becomes a systems question: which processes dominate Earth's redox evolution at different times, and how tightly are they coupled? Only took multiple slow processes running together for the redox ledger to be hard to balance. The narrative returns again to the sea's visible silence because the changes are mostly invisible. A shallow shelf can host microbial mats that trap sediment and alter local chemistry. In the water above, dissolved iron may travel until it meets an oxidant, then precipitate as a faint snow of minerals. Those particles sink, accumulate, and later become rock. In another basin, sulfide may build up and precipitate pyrite, locking sulfur and iron into dark grains. In each case, electrons move, bonds change, and the sea slowly transforms. The same physical water holds a different chemical identity depending on redox. Only took electrons finding new partners for the ocean to become a different ocean. The narrative ends with a soft callback to the project's central theme. Atoms are tiny worlds that resist simplification. An iron atom in seawater is not simply iron. It is iron in a specific oxidation state surrounded by a hydration shell, interacting with ligands influenced by pH, by competing ions, by microbial enzymes, by sunlight. Its fate: stay dissolved, precipitate, become part of a mineral, be reduced again, depends on a network of conditions that can shift quietly. And in that network, Earth's early history is written in the most understated way, not with a sudden announcement of oxygen, but with long redox gradients, patchy oases, slow precipitation, and sediments that record what the water can no longer hold. The central uncertainty remains calm and unresolved. The exact map of early ocean redox through time and space is still being drawn, and the precise contributions of biological and abiotic processes to key deposits remain debate. Yet the transformation is clear in outcome. The ocean becomes a chemical historian, and electron transfers become the ink, and the planet continues to turn, letting atoms do what they always do: follow the rules, form patterns, and reveal in their smallest exchanges how a whole world changes. The ocean's electron exchanges continue, and now the narrative follows the next threshold, where atoms begin to cooperate in a new way, not merely precipitating or dissolving, but organizing into networks that sustain themselves. The accepted fact is that life exists on Earth by at least about 3.5 billion years ago, evidenced by multiple lines of geological and geochemical data, and that life depends on catalytic chemistry. Reactions are accelerated and guided by catalysts, whether mineral surfaces or biological macromolecules, allowing metabolism to proceed in structured pathways rather than as a random scattering of reactions. Life is not a new set of physical laws. It is a new arrangement of chemical possibilities under existing laws. Only took chemistry learning to speed itself up to become the beginning of biology. The narrative remains whisper soft and stays grounded in plausible early environments rather than inventing scenes. It lingers on the kinds of places where gradients are sharp and sustained: hydrothermal systems, porous mineral interfaces, shallow waters with wet-dry cycling along tidal margins, and volcanic landscapes where heat and water meet. The accepted fact is that such environments can concentrate reactants, provide energy gradients, and offer catalytic surfaces. Yet the section's quiet scientific mystery remains central and honest. The origin of life's specific pathway is not fully known. Many plausible steps are demonstrated. In laboratories, formation of amino acids and nucleobases under certain conditions, polymerization on mineral surfaces, lipid self-assembly into vesicles and energy coupling through gradients. But the exact sequence by which Earth's chemistry crosses into Darwinian evolution remains unresolved. Only took the most important transition in Earth history to still lack a single confirmed route. The narrative keeps atoms as the focus by describing catalysis in physical terms. A catalyst lowers the activation energy of a reaction, allowing it to proceed faster at a given temperature without being consumed. Mineral catalysts can do this by providing surfaces where molecules align, bind and react more readily. In modern life, enzymes, protein catalysts, often aided by metal cofactors, do this with remarkable specificity. The accepted fact is that many enzymes depend on metal ions such as iron, nickel, molybdenum, zinc, and magnesium, which participate directly in electron transfer and bond making. This creates a continuity between early geochemistry and later biochemistry metals that cycle in rocks and ocean seas, become embedded in the active sites of enzymes. Only took an iron atom already used to changing oxidation state to become part of metabolism's machinery. A lesser-known real-world detail rests in how some modern enzymes still carry ancient mineral-like clusters, iron-sulfur clusters, for example, that function as electron carriers. These clusters resemble small pieces of mineral chemistry stabilized inside proteins, and they are widespread in life across domains. They are not proof of origin location, but they are a real bridge between inorganic and organic catalysis. Only took life keeping a mineral-like cluster inside itself to blur the boundary between rock chemistry and biology. The narrative remains even and contemplative and introduces a second quiet mystery nested inside the first, the origin of biological information. Replication with heredity requires polymers or systems that can store sequences and be copied with variation. In modern life, nucleic acids fill this role. Many origin of life models explore RNA world scenarios where RNA serves as both catalyst and genetic material, and other models emphasize metabolism-first pathways where chemical networks arise before templated replication is fully developed. The accepted fact is that RNA can act as a catalyst in modern biology, ribozymes showing that nucleic acids can in principle support both function and information. Yet the uncertainty remains how prebiotic conditions produce long information-rich polymers with reliable replication, and how those polymers become enclosed and sustained in environments where hydrolysis and dilution are constant pressures. Only took water being an excellent solvent to also be a quiet enemy of long polymers. The narrative keeps imagery elemental thin films of water evaporating under a warm sun, leaving solutes concentrated on mineral surfaces, then rain returning, dissolving and redistributing, then drying again. Wet-dry cycling is a real process in many environments, and it can drive condensation reactions by removing water favouring bond formation between monomers. This is accepted as a plausible mechanism in some origin of life research, though the relevance of specific environments to early Earth remains debated. A gentle modern analogy can hover restrained, like repeatedly folding and pressing dough, can bring ingredients into closer contact and change their structure. Repeated wetting and drying can bring molecules together and encourage new bonds, though the analogy remains soft. Only took a shoreline breathing in and out with tides to act like a slow chemical press. The ironies arrive softly dry and sleepy. The first irony is that life often associated with activity may begin in places where the most important action is slow concentration and quiet rearrangement. The second irony is that Earth's earliest biology likely thrives in conditions that modern humans would find hostile, anoxic waters, high heat in places, chemical gradients, yet it becomes the foundation for all later comfort. The third irony is that the most profound novelty on Earth begins without intending anything at all. It is chemistry following rules, and yet it produces systems that later appear purposeful. Only took selection operating optimal differences for purpose-like behavior to emerge. The narrative stays grounded and moves into metabolism as electron flow, linking back to the previous section's redox theme without repeating it. Metabolism is at its core controlled electron transfer through a chain of reactions harvesting energy from differences in chemical potential. In modern cells, electron transport chains move electrons through carriers and use the released energy to pump protons across membranes, creating gradients that drive ATP synthesis. The accepted fact is that chemiosmosis using proton gradients across membranes is a central energy mechanism in nearly all life. The deep mystery is whether early life uses similar gradient-based energy systems from the beginning, perhaps exploiting natural proton gradients at alkaline hydrothermal vents, or whether such coupling evolves later. Research explores both possibilities. Only took a difference in pH across a thin barrier to look like a ready-made battery. A lesser-known detail rests in the structure of some alkaline hydrothermal vent systems, where mineral precipitates form thin walls separating alkaline vent fluids from more acidic ocean water, creating natural electrochemical gradients. This has been proposed as a plausible setting for early energy coupling, because the gradients exist without biology and could be harnessed by protocells. Yet the extent to which such settings exist on early Earth, and whether they align with other requirements for polymer formation and replication, remains debated. Only took a natural gradient existing for hypotheses to gather around it. The narrative remains calm and allows the uncertainty to remain a real part of the story. It shifts gently to membranes because compartmentalization is one of the clearest ways chemistry becomes more lifelike. Amphiphilic molecules, those with hydrophilic heads and hydrophobic tails, can spontaneously self-assemble into micelles and bilayer vesicles in water. This is accepted physical chemistry. Such vesicles can encapsulate molecules, maintain internal environments, and provide a surface where reactions can be organized. Yet the mystery persists how early membranes achieve stability and selective permeability, especially in harsh ionic conditions like seawater, and how they integrate with replication and metabolism. Only took molecules with two personalities, water-loving and water-fearing, to build boundaries without plans. A poetic detail rests in the idea that a membrane is a moving boundary rather than a rigid wall. Lipid molecules diffuse laterally. The biliar flexes small molecules pass ions are sometimes excluded, and the boundary breathes in thermal motion. Even in the simplest vesicle, the boundary is alive with physics. Only took atoms jostling at room temperature to make a membrane ripple like a quiet skin. The narrative returns to the question of evidence because Earth history demands grounding. Direct fossils of the very first life are rare and contested. But indirect signals like carbon, isotope fractionation stromatolite-like structures, and microfossil candidates provide constraints. The accepted fact is that many biological pathways, fractionate isotopes and stromatolites, can be built by microbial mats trapping sediment and inducing mineral precipitation. Yet the uncertainty remains especially for the oldest records because abiotic processes can sometimes mimic biological signatures and because metamorphism can alter originals. Only took billions of years of heating and squeezing for early traces to become ambiguous. The narrative keeps one more quiet systems mystery once life exists. How quickly does it diversify metabolically? The tree of life suggests deep branching between major domains, but reconstructing early branches is difficult due to horizontal gene transfer and the lack of a fossil record for microbes. The accepted fact is that horizontal gene transfer is common in microbial evolution, especially early complicating lineage reconstruction. This is a real source of uncertainty. The earliest evolutionary history may be more like a network than a simple branching tree. Only took genes moving sideways for ancestry to become hard to draw as a single line. The narrative ends by returning to the smallest scale again as a soft callback to tiny worlds. An atom of carbon once forged in a star becomes part of a molecule that binds to a mineral surface. A metal ion shuttles an electron in a primitive catalytic cycle. A lipid molecule joins others to form a boundary. A polymer grows by one bond, then another, then folds or breaks. In these small events, the planet's chemistry begins to develop persistence, coupling, and memory. The origin remains unresolved in its precise path, yet the transformation is unmistakable in its outcome. Metabolism appears, replication becomes possible, and Earth's atoms begin to participate not only in rocks and oceans, but in systems that maintain themselves against equilibrium for as long as energy flows. The narrative leaves the main mystery open, as it must. How exactly does chemistry become biology here on this planet at this time? It does not answer. It simply watches the gradients, the catalysts, and the boundaries and lets the slow truth remain that atoms are not simple, especially when they begin to cooperate. Life's catalytic networks continue to spread across surfaces and through water, and as they do, the planet's chemistry begins to shift in a way that is both subtle and vast, because one particular molecule, oxygen, starts as a local byproduct and ends as a global condition. The accepted fact is that oxygenic photosynthesis uses light energy to split water-moving electrons through a chain of reactions and releasing molecular oxygen as a product, and that over geological time this biological oxygen production contributes to a major rise in atmospheric oxygen known as the Great Oxygenation Event, broadly placed around 2.4 to 2.0 billion years ago. The narrative remains whisper-soft and stays close to the physical mechanism, rather than any triumphal story. Photons excite electrons in pigments' charge. Separation occurs, water is oxidized, and oxygen is released. Only took light arriving every day for a new chemistry to be exhaled molecule by molecule. At first, oxygen does not fill the sky. It is consumed. It reacts with reduced gases from volcanism. It oxidizes dissolved ferrous iron in seawater. It attacks sulfides and other reduced minerals. The accepted process is that early Earth contains large oxygen sinks, and for long spans, oxygen production can be balanced by oxygen consumption, preventing atmospheric accumulation, even if oxygen is produced locally. The atmosphere remains largely anoxic, while oases of oxygen exist in shallow waters near photosynthetic communities. This is consistent with many models and proxy interpretations. A lesser-known real-world detail rests in the idea that even a thin film of microbial matter can create steep chemical gradients over millimeters oxygenated water at the surface anoxic conditions just beneath, with redox transitions compressed into a tiny vertical space. The planet's most consequential boundary can at first be the thickness of a fingernail. Only took a few millimeters of chemistry to hold two different worlds at once. The narrative then moves outward from the mat into the ocean where iron travels. When oxygen meets dissolved Fe2, it oxidizes to Fe3 and precipitates as iron oxides or related minerals, removing iron from solution. This is accepted aqueous redox chemistry. Over time, repeated precipitation contributes to iron-rich sedimentary deposits, and the broad association between changing oxygen conditions and banded iron formation deposition is widely accepted even as details remain debated. The sea becomes a place where oxygen's presence is recorded by what it forces out of solution. Only took a new oxidant entering the water for an entire element to change its preferred form. The narrative holds the section's quiet scientific mystery gently and precisely. Why does oxygen accumulate globally when it does? Many hypotheses are studied, and the best view is that multiple processes interact changes in biological productivity, nutrient delivery, and organic carbon burial. changes in volcanic gas composition and mantle redox state, the saturation or decline of oxygen sinks, and the long-term loss of hydrogen to space, which can oxidize the surface environment over time by reducing power. Evidence supports a rise in oxygen, but the relative weights of these drivers and the exact tipping sequence remain uncertain. Only took a planet-sized ledger of sinks and sources to make the timing of oxygenation a problem with more than one plausible solution. The narrative stays grounded in the strongest markers for atmospheric change. One of the key accepted facts is that sulfur isotopes in ancient rocks show mass-independent fractionation MIF signatures under very low oxygen atmospheric conditions produced by ultraviolet photochemistry, and that these signatures largely disappear from the rock record around the time of the Great Oxygenation Event, indicating a fundamental shift in atmospheric chemistry. The detail is quiet and beautiful in a restrained way. Sunlight writes one kind of isotopic pattern when the sky is chemically permissive, and a different sky makes that writing stop. Only took oxygen changing the atmosphere's photochemistry for the sun's isotopic handwriting to vanish from new sediments. Another accepted proxy is the appearance of oxidized terrestrial sediments and changes in iron mineralogy that suggest more oxidative weathering on land as oxygen rises. Yet even these signals are not perfectly synchronous everywhere. The planet is large and the record is patchy. The uncertainty remains in the texture of the transition. Is oxygenation smooth-stepped, pulsed, regionally variable with possible overshoots and retreats? Many studies suggest complexity rather than a single clean step. Only took Earth refusing to be uniform for a great event to behave like a long drift with pauses. The narrative keeps the atmospheric chemistry calm and physical. Oxygen is reactive and its presence changes what gases can persist. Methane, a strong greenhouse gas that can be more abundant in anoxic atmospheres, becomes less stable as oxygen rises because it is oxidized more readily. A reduction in methane can cool the planet, potentially contributing to glaciations in the Paleo-Proterozoic, though the magnitude and coupling remain debated. This is a plausible linkage discussed in Earth system science. The quiet mystery here is how tightly climate responds to changing methane in the context of other greenhouse gases, cloud behavior, and tectonic influences. Only took one gas becoming scarce for the temperature balance to become sensitive in a new way. A gentle modern analogy can hover restrained, like removing a thin insulating layer from a warm surface. Reducing methane can allow more heat to escape, though the analogy remains soft because atmospheric radiative transfer is wavelength specific and non-linear. The narrative lingers on the changes oxygen makes to minerals because minerals are atoms arranged under certain rules, and oxygen changes the rules of stability at the surface. With more oxygen, certain reduced minerals become unstable and weather more readily, while oxides and hydroxides become common products. Iron transitions from being broadly mobile in reduced form to being rapidly scavenged and precipitated. And this affects nutrient availability because iron is a critical micronutrient for many metabolic processes. This is accepted biogeochemical reasoning. Redox state influences trace metal solubility and delivery, yet the details remain uncertain. How does the rise of oxygen reshape nutrient limitation in early oceans? And how does that feedback on productivity and oxygen itself? Only took one element solubility changing to influence the pace of life's own atmospheric transformation. A lesser-known detail rests in the chemistry of molybdenum and other trace metals that become more available in oxygenated environments and are important for enzymes like those involved in nitrogen fixation. The degree to which rising oxygen increases trace metal availability and how that affects the nitrogen cycle and productivity is still studied through proxies and models. It is a quiet reminder that oxygenation is not only about oxygen, It is about a suite of link cycles. Only took a trace metal becoming slightly more mobile to matter at planetary scale over time. The ironies arrive softly dry and sleepy without any spike in tone. The first irony is that oxygen, later treated as the symbol of breath, begins as a waste product for organisms that do not need it and often cannot tolerate it. The second irony is that the atmosphere's transformation is built by tiny cells that cannot see the sky they are changing, working at the scale of micrometers, while the consequences unfold across a whole planet. The third irony is that oxygen's rise makes some environments more hospitable and others less so. Progress, if it is called that, is simply reconfiguration. Only took a new chemistry spreading for winners and losers to be written into redox gradients. The narrative keeps the pacing slow and returns to the physical inevitabilities. If oxygen is produced and organic carbon is buried, removed from rapid oxidation, then oxygen can accumulate because burial prevents immediate recombination of reduced carbon with oxygen. This is an accepted conceptual framework. Oxygen accumulation is linked to the balance between oxygen production via photosynthesis and oxygen consumption via respiration and oxidation, with organic carbon burial acting as a long-term lever. Yet quantifying burial rates in deep time is difficult, and the sedimentary record that might constrain them is incomplete and altered. The uncertainty remains in the numbers even when the direction is clear. Only took the ocean burying some carbon instead of recycling it immediately for the atmosphere to change slowly. The narrative also holds the role of tectonics without turning it into a separate story. Continental growth and weathering influence nutrient delivery, especially phosphorus, which can limit productivity over long times. Volcanic outgassing composition depends on mantle conditions and influences atmospheric redox. Subduction recycles oxidized and reduced materials. These are accepted couplings in Earth system science, yet the early Earth's tectonic style and continental area are not perfectly known. The quiet mystery remains: how do tectonic evolution and biological evolution co-steer oxygenation, and which changes lead versus follow at key moments? Only took Earth having multiple moving parts to make causality hard to isolate. The narrative ends with a calm image of the sky becoming subtly different over long spans. Oxygen is still a trace gas compared to nitrogen, but trace gases matter. As oxygen rises, ozone forms in the upper atmosphere, absorbing ultraviolet radiation and altering photochemistry. The surface's ultraviolet environment changes, influencing both chemistry and biology. The planet's colors change too slowly. Iron-rich seas become less common as dissolved iron is removed. Oxidized soils redden. The chemistry of rivers shifts. None of this happens with a single sunrise. It happens with a long accumulation of tiny acts: photons captured, electrons moved, water, split oxygen released, sinks, slowly filled burial, slowly storing reduced carbon away from immediate oxidation. The uncertainty remains unforced and honest. The exact timing, pacing, and dominant drivers of oxygenation are still being refined, and the early Earth's patchwork redox landscape is difficult to reconstruct perfectly. Yet the transformation is clear in outcome. Oxygen becomes a persistent participant in Earth's surface chemistry, and atoms that once behaved one way in an anoxic world now find new constraints and new opportunities in an oxidizing one. The tiny worlds inside matter reveal again that simple is never adequate. A single molecule's rise reshapes minerals, climates, and the future possibilities of life, all through the quiet discipline of electrons obeying the rules they always follow. Oxygen now lingers as a background condition in more places, and life responds not with a single leap but with a reorganization of interiors, because one of the most consequential transformations in Earth's biological history happens at a scale too small to see a cell begins to contain another cell as a permanent partner. The accepted fact is that eukaryotic cells arise through endosymbiosis, with mitochondria descended from an ancestral bacterium that becomes an organelle inside a host lineage, and this is supported by converging evidence mitochondria have their own DNA. Their ribosomes and membranes show bacterial affinities. Their genes and proteins place them within bacterial phylogeny, and their double membrane structure is consistent with an engulfment origin. The narrative remains whisper-soft and stays close to physical reality. Membranes touch gradients, form electrons, move, and energy becomes more available per unit of food and oxygen. Only took one relationship refusing to end in digestion for the energetic budget of life to change. The ocean remains the quiet stage because early eukaryotes live in water long before they are anything large. The Proterozoic sea is not uniform. It is layered in many basins with oxygenated surface waters in some regions and anoxic, deeper waters in others, according to many proxy interpretations, though. The extent and persistence of this stratification across the whole planet remain uncertain. In that layered ocean, a partnership that relies on oxygen can still thrive near interfaces where oxygen is present but not overwhelming, and it can also adapt in lineages that later evolve modified mitochondria in low oxygen settings. The accepted point is that mitochondria are central to eukaryotic metabolism even when oxygen is scarce, because mitochondria-related organelles exist across eukaryotes in many environments showing deep ancestry. Only took oxygen being patchy for the earliest complex cells to find margins rather than perfect conditions. The narrative lingers on what mitochondria do because the story of tiny worlds becomes literal again inside a cell. Mitochondria maintain an electrochemical gradient across an inner membrane by moving electrons through an electron transport chain, using the released energy to pump protons and then allowing protons to flow back through ATP synthase to produce ATP. This is accepted bioenergetics. It is a disciplined use of gradients, a controlled leak that becomes power. The inner membrane folds into cristae, increasing surface area for these reactions, and the shape and density of cristae vary across organisms, reflecting different energetic demands. A lesser-known real-world detail rests in how these folds can shift with metabolic state, becoming more elaborate when energy demand is high and simplifying when it is low, as if the organelle quietly rearranges its internal landscape to match the cell's needs. Only took a membrane folding like a quiet accordion to multiply the area where energy is made. The narrative remains calm and introduces the section's central scientific mystery. In a precise, honest way, the exact sequence of steps in eukaryogenesis is still debated. Did a host cell with a cytoskeleton and some internal complexity already exist capable of engulfment and membrane remodeling and then acquire mitochondria? Or does the mitochondrial acquisition occur early and provide the energetic surplus that allows the later evolution of complex internal regulation and larger genomes? Genomic evidence strongly supports that the host lineage is archaeal and that eukaryotes are chimeras with archaeal informational machinery and bacterial metabolic contributions, yet the ordering of events and the ecological context remain unresolved. Only took the most important merger in cellular history to keep its choreography partly hidden. The narrative stays grounded by touching a modern line of evidence without treating it as a plot twist. Genomic surveys reveal archaeal lineages with genes related to eukaryotic-like cytoskeletal and membrane trafficking functions, supporting the broad picture that eukaryotes arise from within the archaeal domain, and that complexity has deep roots in microbial diversity. Yet these discoveries do not provide a complete fossilized sequence of steps. They provide hints of capability and ancestry. The uncertainty remains what exact cellular behaviors exist in these ancestral lineages, how they interact ecologically with bacteria, and which interactions make a stable endosymbiosis likely. Only took sequencing hidden microbes to make the origin feel closer and still not fully captured. The narrative lets the physical constraints remain the focus. A stable endosymbiosis requires more than proximity. It requires compatibility, avoidance of host digestion, regulation of internal environment, exchange of metabolites, and over time, integration of genetic control. One accepted process is endosymbiotic gene transfer. Genes from the endosymbiont move to the host genome, and proteins encoded in the host are targeted back to the organelle, making the organelle dependent on the host and the host dependent on the organelle. This creates irreversibility. It is not a friendship that can be ended without consequence. It becomes a single system. Only took genes changing addresses for two organisms to become one lineage. A poetic detail rests in the quiet way this integration leaves traces today. Mitochondrial genomes are small compared to bacterial genomes, and many mitochondria keep only a subset of genes involved in core functions. Why certain genes remain in mitochondria while others transfer to the nucleus is an active topic, with hypotheses involving local control of redox-sensitive components, hydrophobicity of proteins, and protection from oxidative damage, among others. The uncertainty is real. The rule for gene retention is not fully settled. Only took a handful of genes staying behind to keep a long debate alive. The ironies arrive softly dry and sleepy without any spike in tone. The first irony is that the rise of complex life depends on an invasion that becomes a necessity, turning what looks like an accident into architecture. The second irony is that the cell's greatest power supply is also a source of reactive oxygen species, meaning that the organelle that enables high-energy metabolism also produces byproducts that can damage molecules, forcing cells to evolve antioxidants and repair systems. The third irony is that the most profound reorganization of life's complexity occurs while life remains mostly microscopic for a very long time afterward, as if the planet installs new machinery and then waits. Only took 1 billion years or so for the upgrade to become obvious at the surface. The narrative stays slow and returns to the broader Earth system because mitochondria and oxygen are linked by availability and by energy yield, yet the relationship is not a simple on-off. Aerobic respiration yields far more ATP per molecule of organic substrate than many anaerobic pathways, which can support larger genomes and more elaborate regulation. But eukaryotes also inhabit low oxygen niches and can use alternative pathways. The accepted fact is that mitochondria are flexible and that eukaryotic metabolism is diverse. The quiet mystery remains in Earth history. What were oxygen levels through much of the Proterozoic, and did oxygen availability limit the expansion of eukaryotes, or were other factors? Nutrients, ecological interactions, predation, and genetic innovations more decisive. Proxy records suggest oxygen remains below modern levels for long spans, but precise values and variability remain debated. Only took oxygen being enough sometimes to make constraint hard to quantify. A gentle modern analogy can hover restrained like a town that can grow when energy supply becomes steadier. A cell can expand its internal operations when ATP production becomes more abundant and controllable, though the analogy remains soft because evolution does not plan growth. It selects what works. The narrative then lingers on the ecological consequences of having mitochondria, because energy changes how cells can behave. Eukaryotes can afford dynamic cytoskeletons, endomembrane trafficking, phagocytosis, and complex life cycles in many lineages. These capabilities reshape food webs. Larger cells can graze on bacteria, predation can intensify selection, and microbial ecosystems become more interactive. The accepted fact is that eukaryotic predation and grazing exist and can restructure microbial communities. In deep time, this likely contributes to changes in carbon cycling and sedimentation, though quantifying it remains difficult. Only took one cell learning to eat another efficiently for ecology to become more complicated. A lesser-known, real-world detail rests in microfossils often grouped as acritarchs, organic-walled microfossils that become abundant in Proterozoic rocks and are widely interpreted as eukaryotic in many cases. Their ornamentation spines ridges. Complex walls suggests interactions with the environment, potentially including defense against grazers or changes in buoyancy and life cycles. These shapes are not decoration, they are physics and ecology expressed in wall structure. Yet the earliest timing and interpretation of specific forms can be uncertain, because preservation varies and morphology can be ambiguous. Only took a tiny spine on a microscopic sphere to hint that something in the water is now worth defending against. The narrative keeps the atom-centered theme by returning to membranes and gradients because mitochondria are a second layer of boundary making inside the cell. Earlier membranes appear as the first compartments. Now internal membranes multiply compartments, nucleus, mitochondria, endoplasmic reticulum vesicles. Each boundary allows different chemistry to be maintained side by side. This compartmentalization is an accepted hallmark of eukaryotic cells. Yet the quiet mystery remains why certain organizational patterns emerge repeatedly in evolution, and how physical constraints, diffusion limit surface area needs, redox management shape what is favored. Only took diffusion being slow over larger distances for compartments to become useful. The narrative slows further and returns to the material truth that keeps everything grounded. Earth's atoms continue to obey the same rules. Iron-sulfur clusters shuttle electrons in enzymes. Phosphates store energy in ATP. Oxygen accepts electrons at the end of respiratory chains. Protons create gradients across membranes. The newness is not in the laws, it is in the arrangement. Two lineages become one integrated system, and that system becomes a platform for further complexity. The uncertainty remains calm and unresolved. Which exact ecological setting hosts the first stable mitochondrial endosymbiosis? What sequence of cellular innovation surrounds it? And how oxygen landscapes in Proterozoic oceans shape its spread? The narrative does not resolve those questions, it simply stays with the quiet scene of a cell containing an internal engine, drifting in water, dividing, carrying within it an ancient bacterial ancestry now folded into a new kind of life. In that contained partnership, atoms prove again that they are not simple, because when they are arranged into gradients and membranes and electron pathways, they build tiny worlds inside cells that eventually change what a planet can become. The planet now carries oxygen more often near the surface, yet the story of atoms refuses to stay confined to cells because the same interactions that fold a membrane also decide whether an ocean freezes. The narrative turns to phase to the way matter changes its state when pressure and temperature cross thresholds, because Earth's greatest climate swings are in the end atomic negotiations, water molecules choosing solid lattices or liquid motion carbon dioxide, choosing gas or mineral salts, changing freezing points, rocks storing heat and releasing it slowly. The accepted fact is that phase transitions occur when thermodynamic conditions shift, and that for water on Earth, the transition between liquid and ice strongly affects planetary energy balance, because ice reflects much more sunlight than liquid water, and dark rock creating an ice albedo feedback that can amplify cooling. This is a core principle in climate science. Only took water turning white to teach the planet how to cool itself faster. The narrative remains whisper soft and stays close to physical surfaces. Snow and ice spread across a continent, then across a shelf, then across open water. Each new patch of bright surface reflects more incoming sunlight, lowering absorbed energy, encouraging more freezing. The feedback is not intelligent, it is simple. Yet its consequences can be enormous over long time. The accepted fact is that Earth has experienced major glaciations in the Proterozoic, including events often grouped under the term snowball Earth, particularly during the Cryogenian period when evidence suggests ice reaches low latitudes. This evidence includes glacial deposits found at paleolatitudes near the tropics inferred from paleomagnetism and sedimentary features consistent with glacial environments. Only took ice reaching the wrong latitude to make a warm world assumption collapse. The narrative lingers on water's molecular behavior because ice is not merely cold water, it is a structured lattice. In common ice, water molecules arrange into a hexagonal network held by hydrogen bonds, and that network is unusually open, making ice less dense than liquid water and allowing it to float. This is accepted physical chemistry. The floating of ice is not a decorative fact. It changes how freezing proceeds, because ice forms a surface lid that insulates the water beneath, slowing complete freezing and allowing liquid water to persist below in many settings. Only took ice floating for lakes and oceans to keep dark water beneath a bright skin. A lesser-known real-world detail rests in the existence of many ice phases under pressure, Ice C to Ice 3, and others with different crystal structures, reminding that even a familiar molecule like H2O has multiple solid identities. On Earth's surface, the hexagonal form dominates, but in deep ice sheets and under high pressures, subtle transitions can occur, and in planetary interiors elsewhere, different ice phases become common. The narrative keeps this as a quiet note: even ice is not one thing. Only took pressure rearranging hydrogen bonds for the same water to become a different solid. The section's quiet scientific mystery sits naturally here, because the idea of a fully frozen ocean raises questions that are still actively studied. How severe are snowball Earth events exactly? Do glaciers and sea ice cover nearly all oceans, leaving only small polyneas or none at all? Or does the planet enter a slushball state with open equatorial waters while ice dominates elsewhere? Both kinds of models can produce low-latitude glacial evidence under different conditions, and the rock record provides constraints but not a single perfectly unambiguous answer. The severity matters because it affects ocean circulation, biological refugia, and how quickly deglaciation can occur. The narrative does not decide, it holds the uncertainty as a real boundary. The planet's ice extent during these events is still debated. Only took an ancient glacier leaving deposits without a global map attached to keep the question open. The narrative remains grounded by turning to carbon dioxide because the path out of global ice, if it occurs, must be physical. The accepted mechanism often discussed is that during widespread glaciation, silicate weathering on land is greatly reduced because rocks are covered by ice and liquid water is limited, while volcanic outgassing of CO2 continues, allowing atmospheric CO2 to accumulate over time. As CO2 rises, greenhouse warming eventually becomes strong enough to melt ice, especially near the equator, triggering a rapid deglaciation once albedo feedback reverses. This is an accepted conceptual framework in many snowball Earth models. Only took weathering shutting down while volcanoes keep breathing for the sky to slowly thicken with heat-trapping gas. A poetic detail appears in the sediments that may follow deglaciation carbonate layers, sometimes referred to as cap carbonates, deposited rapidly after glacial episodes, often with distinctive textures. Their formation is linked to drastic changes in ocean chemistry and carbon cycling. As ice melts, seas rise and weathering resumes. The details of their exact formation conditions are complex, but their presence is a quiet stone signature that the planet swings between extremes and then deposits a new chemical skin. Only took a thaw to leave a bright layer of carbonate like a pale bandage on the rock record. The narrative keeps atoms at the center by noticing that salinity and dissolved ions influence freezing too. Seawater freezes differently than pure water because dissolved salts lower the freezing point and because brine rejection during sea ice formation increases salinity and density of underlying waters influencing circulation. This is accepted ocean physics. In a near-global ice scenario, brine dynamics could shape where ice thickens and where liquid persists. Yet reconstructing the exact salinity and stratification of cryogenian oceans is difficult, and proxy constraints are limited. The uncertainty remains: what is the chemical state of the ocean during these glaciations, and how does it affect ice dynamics and life? Only took salt refusing to join the ice lattice to complicate a planet's freezing behavior. The ironies arrive softly dry and sleepy without disturbing the calm. The first irony is that water's most familiar habit, freezing, can under the right feedbacks become the planet's most destabilizing climate behavior. The second irony is that a world can become nearly all ice while volcanoes continue to erupt beneath it, heat rising into a system that from above looks silent and sealed. The third irony is that the evidence for global-scale freezing is carried by rocks that are later warmed, deformed, and moved by tectonics, meaning the planet tries to erase the very clues needed to understand how extreme it once becomes. Only took a tectonic plate doing its job to make paleoclimate reconstruction harder. The narrative turns gently to stone again because phase changes do not belong only to water. In metamorphism, minerals change phase as temperature and pressure rise, rearranging atoms into new structures without melting completely. This is accepted geology. Metamorphic faces reflect stable mineral assemblages under certain pressure-temperature conditions, and these transitions can release or absorb fluids, influence rocks' strength, and affect tectonic behavior. Deep in subduction zones, water bound in minerals can be released as pressure and temperature change, fueling melting and volcanism. The planet's phase transitions are therefore not only climatic, they are tectonic and chemical. Only took a mineral letting go of its water at depth to feed magma that later returns gases to the surface. A lesser-known detail rests in how some phase boundaries inside Earth are sharp enough to reflect seismic waves, creating discontinuities like the ones near 410 and 660 kilometers depth, associated with transformations of olivine and related minerals. These are real and mapped globally. They are reminders that the mantle is not a uniform solid, it is layered by atomic rearrangements. Only took the same atoms packing differently to create a boundary that can be heard through earthquakes. The narrative keeps a gentle modern analogy restrained like a thermostat that triggers a change in a heating system once a threshold is crossed. Phase transitions can make Earth respond non-linearly when conditions pass certain limits. Though the analogy stays soft because Earth has no intent and no set point. The key idea remains: thresholds matter because they flip feedbacks. The narrative returns to snowball Earth's unresolved details one last time, without repetition, focusing on the quiet question of survival. If oceans are largely ice-covered, how does life persist? Proposed refugia include hydrothermal vents, cracks, and thin ice regions, equatorial polyneas, sub-ice photosynthetic zones where light penetrates, and microbial life in brine, channels within sea ice. These are plausible and consistent with life's resilience and with modern analogues, yet direct evidence for specific refugia in the cryogenian is limited. The uncertainty remains: what ecological pathways bridge extreme glaciations to later diversifications. Only took life being mostly microbial for survival options to be many and still hard to confirm in stone. The narrative stays slow and notices that phase transitions are in a way Earth's method of compressing time into events. Long periods of gradual forcing can lead to sudden changes in state ice advances. Ice retreats, minerals transform, gases accumulate then decline. The planet does not change smoothly all the time. It changes with thresholds that are built into matter's rules. Water chooses a lattice at one temperature, a liquid at another. Carbon chooses a gas in one context, a rock in another. The same atoms participate in different worlds depending on state. Only took a few degrees and a feedback loop for a planet to look completely different. The section ends with a calm image of ice under a dim sun, not as a dramatic apocalypse, but as a physical regime. A wind blows over a white surface. Beneath, the ocean remains moving slowly, carrying salts and dissolved carbon, receiving heat from the interior. Volcanoes continue to release gases even if they emerge through ice or beneath water. Somewhere chemistry continues and tiny cells continue their patient metabolisms along gradients that do not care about latitude. The exact extent of the ice remains uncertain, and the precise pathway of deglaciation and recovery remains under study. But the central transformation is clear. Phase changes, and feedbacks can push Earth into climates far from the modern one, and these extremes are made possible by the same simple-seeming molecule. Water obeying the deep rules of hydrogen bonding and thermodynamics. Atoms again reveal their depth, they build lattices, they trap heat, they flip albedo, and they allow a planet to freeze and thaw in slow, lawful cycles that remain partly mysterious in their most extreme details. The ice retreats in the imagination. The ocean returns to darker tones and the narrative drifts inward again, because after climates and continents and cells, it is still the smallest rules that decide what can be seen at all. The story returns to the quantum edge, where atoms are both particles and waves, and where the classical world that feels smooth is an emergent convenience. The accepted fact is that quantum systems can exist in superpositions of states, and that interference effects are observable when coherence is preserved, while in everyday macroscopic conditions interactions with the environment cause rapid decoherence that suppresses observable interference, making objects behave classically. This is a standard part of modern quantum physics supported by experiments across many platforms. Only took the environment constantly touching everything for the universe to look definite most of the time. The narrative remains whisper soft and stays grounded by tying this to matter that builds Earth. A mineral grain is a warm, vibrating assembly of atoms. Its electrons are still described by quantum mechanics, and its lattice vibrations can be treated as quantized excitations called phonons. Yet the grain behaves as a classical object because it is never isolated. It exchanges photons with its surroundings, collides with other molecules, and bathes in thermal noise. The accepted process is that coupling to many degrees of freedom destroys phase relationships that would allow macroscopic superpositions to remain observable. Earth's surface is therefore a decoherence engine, turning quantum possibility into classical stability at every moment. Only took air molecules and thermal vibrations to enforce the everyday world's certainty. A poetic detail rests in the quiet way crystals reveal their quantum origins without appearing strange. A diamond's hardness arises from covalent bonding and electron sharing in a specific lattice structure. A metal's conductivity arises from electron bands extending through a crystal. A semiconductor's behavior arises from a band gap that controls which electron energies are allowed. These are accepted. The world's most tactile properties, hardness, brittleness, conductivity, color, are macroscopic echoes of quantum structure. Only took electrons arranging into bands for a wire to feel ordinary, while behaving like a collective quantum system. The narrative holds the section's central quiet mystery in a careful, honest way. What exactly is measurement in quantum mechanics? Quantum theory provides precise rules for predicting outcomes, and their probabilities and decoherence explains why interference disappears in practice. Yet the emergence of a single definite outcome from a superposition remains interpretively unsettled. Different interpretations describe this differently, and no consensus exists on what the wave function fundamentally represents, whether it is a real physical entity, a state of knowledge, or something else. This is not an uncertainty about predictions, it is an uncertainty about meaning. Only took the most successful theory in physics to still leave room for multiple stories about what its symbols are. The narrative stays calm and lets this mystery remain a horizon, rather than a problem to solve tonight. It returns to Earth science as a grounded parallel. Earth's past is known through measurements, and measurements are interactions that yield definite outcomes, numbers, spectra, isotope ratios, yet the world that produces them is always richer than the measurement. A mass spectrometer counts ions, a spectrometer counts photons, a seismometer counts vibrations, a microscope counts reflected light. Each instrument converts physical interactions into records. In that sense, knowledge of both atoms and Earth history is built on outcomes on what survives as a detectable trace. Only took a detector registering a pulse to make deep time a number. The ironies arrive softly dry and sleepy without changing the even tone. The first irony is that atoms feel like the simplest parts of matter, yet they require probabilistic mathematics to describe even their most basic behavior. The second irony is that the macroscopic world feels solid and certain, even though it is built from entities that do not behave like solid and certain things when isolated. The third irony is that humans trust quantum theory enough to build technologies, lasers, transistors, atomic clocks, while still disagreeing about what the theory means beneath the calculations. Only took practical success to coexist with philosophical unfinishedness. The narrative stays slow and touches one more accepted process that links quantum behavior to timekeeping without repeating earlier. Dating discussion. Atomic clocks work because electron transitions between specific energy states occur at extremely stable frequencies, and by counting these oscillations, time can be measured with extraordinary precision. This is accepted. It is a quiet reminder that quantization is not merely an abstract idea, it becomes a tool so precise that it defines modern time standards. Yet even atomic clocks rely on repeated measurement and on averaging because individual quantum events remain probabilistic. Only took a single transition being stable to make timekeeping more precise than Earth's rotation. A lesser-known real-world detail rests in how interference and coherence are preserved in certain carefully controlled systems, such as superconducting circuits or trapped ions where temperatures are lowered and environmental noise is minimized. These systems can maintain quantum states long enough to demonstrate behavior that would otherwise be washed out. They show that classical is not a fundamental category, it is a regime that emerges under ordinary conditions. The narrative keeps this detail gentle because the series remains anchored in Earth. These experiments require isolation that Earth's surface rarely provides. Only took a laboratory becoming nearly silent to allow the quantum whisper to be heard. The narrative now returns to the atom as tiny world in the most literal sense. The electron in an atom is not a point orbiting like a planet. It is a quantum object described by a wave function, with probability distributed in space and with angular momentum and other properties quantized. This is accepted. Yet even this familiar statement contains subtlety in many electron atoms. Electron-electron interactions create correlations that can be complex, and many properties require approximations and computational methods to solve. The uncertainty is not whether quantum rules apply, but how best to represent and calculate the full many-body behavior in different contexts. Atoms, molecules, solids, liquids. Only took more than one electron existing to turn exact solutions into rare exceptions. A gentle modern analogy can hover restrained, like predicting a single pendulum is straightforward, but predicting a room full of coupled pendulums becomes complex. Predicting hydrogen is simple, while predicting a complex molecule or solid becomes a many-body challenge, though the analogy remains soft. The narrative keeps the flow continuous and returns to decoherence as a quiet gate between quantum description and classical experience. The environment does not choose outcomes. It entangles with the system, distributing information about the system's state into many degrees of freedom, making interference between alternatives effectively inaccessible. This is accepted in the decoherence framework. Yet whether this fully explains the appearance of a single outcome, or whether something else is needed, conceptually remains debated. The narrative does not take sides. It remains neutral as required, letting mystery remain. Only took information spreading into the environment for alternatives to stop interfering, leaving a world that looks like one history rather than many. The narrative then ties this to Earth's record one last time softly. Earth's rocks are classical archives. They keep isotope ratios, crystal defects, mineral assemblages. They do not preserve quantum superpositions. They preserve outcomes of countless interactions. Yet the rules that determine which minerals exist and which isotopes decay are quantum. In that way, Earth history is an emergent classical story written by Quantum Inc. The planet's solidity is not a denial of quantum behavior. It is the result of it under constant environmental contact. Only took trillions of quantum events per second to produce a world that feels stable enough to stand on. The section ends with a quiet, unforced pause around the central unresolved question. Measurement is everywhere in practice, photons scattering off surfaces, molecules colliding, detectors counting, memories forming. The mathematics of quantum theory handles these interactions with precision, yet the interpretation of what collapse or outcome fundamentally is remains open in multiple coherent frameworks. The narrative does not seek closure. It simply lets the atom remain deep, a system that can be precisely predicted statistically, that can be harnessed technologically, that builds crystals and oceans and life, and that still at its foundations resists a single final story about what happens between possibility and fact. In that resistance, the tiny world of the atom keeps its quiet complexity, and the planet that arises from trillions of such tiny worlds continues to feel simple only from far away. The narrative now eases back from the quantum edge without closing it, returning to Earth's surface where the smallest rules become the largest textures, because the point is not to solve atoms into simplicity, but to notice how their depth sustains every calm, tangible thing. The accepted fact is that the macroscopic properties of materials' strength, elasticity, conductivity, heat capacity, magnetism emerge from atomic structure and interactions, and that these properties can be explained and predicted through frameworks that connect quantum behavior to bulk matter, from solid-state physics to thermodynamics. A continent's rigidity, a metal's shine, a clay's softness, a glacier's creep, each is the collective outcome of tiny worlds moving and aligning and resisting in patterned ways. Only took countless atoms agreeing on a lattice for stone to feel reliable under a footstep. The narrative remains whisper soft and lets that reliability become the final sustained image. A rock is a frozen negotiation among atoms, but it is not perfect. Crystals contain defects, and defects are not flaws. They are the reason rocks deform rather than shatter under tectonic stress. The reason metals can be bent, the reason diffusion can occur. Dislocations, line defects in crystal lattices allow minerals and metals to deform plastically under stress. This is accepted materials, science and mineral physics. In Earth's mantle, creep occurs through mechanisms like dislocation creep and diffusion creep, depending on stress, temperature, grain size and water content. Plate tectonics is therefore in part a story of defects moving through crystals over millions of years. Only took a line defect sliding through a lattice for a whole plate to drift a few centimeters per year. A lesser-known, real-world detail rests in the way tiny amounts of water in mantle minerals can dramatically affect viscosity by weakening bonds and enhancing defect mobility, influencing convection and plate behavior. Water in the mantle does not always exist as liquid. It can be stored as hydroxyl in mineral structures, especially in certain high-pressure phases. This is accepted nominally, anhydrous minerals can contain water in defects. Yet the distribution and total inventory of deep mantle water remain uncertain, constrained by experiments, inclusions in diamonds and geophysical inferences. The quiet mystery here is how much water is stored deep and how it cycles over time. Only took hydrogen hiding in defects to make dry rock an incomplete description. The narrative holds the three soft ironies dry and sleepy as the closing section settles. The first irony is that the planet's slowest motions mantle convection plate drift depend on tiny imperfections, meaning Earth's grand geology relies on being slightly broken at the atomic scale. The second irony is that atoms obey deterministic equations for energy levels and bonding patterns. Yet many outcomes, like when a nucleus decays, or which exact defect moves first, retain probabilistic character, and the world still becomes reliable at large scale. The third irony is that humans call atoms building blocks as if they are bricks, yet bricks are simpler than atoms, and the analogy only survives because atoms are so consistently strange that the mind needs metaphors to stand near them. Only took the simplest metaphor, being wrong, to still be useful. The narrative remains calm and returns to chemistry's continuity across time. The periodic table's structure arises from electron shells and quantum rules, and that structure governs which minerals exist, which gases persist, and which biochemical pathways are possible. Silicon and oxygen dominate crustal minerals because of their bonding and abundance. Carbon becomes the backbone of life because of its versatile bonding geometry and energetics. Iron becomes central to metabolism and geology because it readily changes oxidation state and is abundant. Phosphorus becomes central to energy transfer because phosphate bonds store usable free energy in ATP and stabilize genetic backbones in nucleic acids. These are accepted generalities in geochemistry and biochemistry. Only took a few elements having the right bonding behaviors for the planet to become both rocky and alive. Yet even with this continuity, the narrative keeps one final quiet uncertainty present, whether there is a deeper, more unified description that will make quantum foundations feel less interpretively open. Quantum mechanics works, but its connection to gravity and spacetime is not yet fully integrated into a single experimentally confirmed framework. The search for quantum gravity, for a consistent theory that unites the quantum with general relativity, remains ongoing. The narrative does not speculate beyond consensus. It simply notes that the foundations are still being explored. Only took gravity refusing to quantize straightforwardly to keep fundamental physics unfinished. A gentle modern analogy can hover restrained, like knowing a language fluently while still debating the origin of its grammar. Physics uses quantum rules expertly while still debating what those rules fundamentally say about reality. The analogy remains soft and does not overreach. The narrative returns to Earth's oceans one last time, because the script began with stone and moved through water and light and time. The ocean remains a vast electrolyte carrying ions and heat interacting with basalt at ridges dissolving and precipitating minerals, moderating climate through carbon chemistry. The atoms in the sea are not separate from the atoms in rock. They exchange continuously. The atmosphere remains a thin mixture shaped by the molecular spectra and by redox cycles. Life remains a chemical network powered by gradients and catalysts built from the same elements forged in stars. The planet remains in every sense a circulation of atoms. Only took a few billion years for the surface to look stable while everything keeps moving. A lesser-known real-world detail rests in the fact that even the air's most common gas, nitrogen, is not inert in the grand story. Its fixation into biologically usable forms requires energy-intensive processes and certain enzymes that fix nitrogen use complex metal cofactors. The nitrogen cycle couples to oxygen levels, productivity and climate over time. It is a reminder that the atmosphere's background gases participate in deep time through chemistry and biology. Yet the detailed history of Earth's nitrogen cycle in the Proterozoic and earlier remains uncertain, constrained by proxies that are still being refined. Only took a background gas requiring special chemistry to become a hidden lever in planetary evolution. The narrative remains whisper-soft and begins to remove forward motion, preparing for rest without summary. It stays with the idea that atoms are not tiny, simple dots. They are quantized systems whose behaviors scale into every feature of Earth history. They make minerals by repeating lattices. They make time by decaying in predictable averages. They make oceans salty by dissolving and traveling as ions. They make climate sensitive by absorbing and emitting light in bands. They make life possible by forming bonds that can store information and by moving electrons through controlled pathways. And they remain even now partly mysterious in meaning at the deepest level, not because knowledge fails, but because the universe's foundations are still being examined. Only took understanding so much to see clearly what is still unknown. The section ends with an image that holds Earth and the atom together in quiet alignment. Night rests over a coastline. The sea quietly shifts molecule by molecule under moonlight. The rocks below hold crystal lattices full of defects that enable them to creep and fracture over time. Within those rocks, a small number of nuclei decay, releasing a whisper of heat and a record of time. In the air above, molecules absorb infrared and re-emit it, regulating temperature with invisible bands. In living cells nearby, membranes hold gradients. Enzymes move electrons, DNA holds sequences. Mitochondria fold their membranes and make ATP. Nothing in this scene violates the laws. Nothing needs an extra story to happen. The complexity is already present, built into the tiny worlds of atoms and into the long patience of Earth. The rhythm slows further now, and the narrative releases the urge to move forward. Earth remains as a steady presence, not as a conclusion, but as a continuing arrangement of matter and energy that does not need to be simplified to be understood. The ocean keeps circulating, carrying ions in wide loops, and the air keeps pressing gently against every surface, a thin mixture of molecules whose invisible spectra shape warmth and cold. Stone keeps its lattices, and within those lattices defects drift over geologic time, letting mountains rise and soften, letting plates glide by centimeters each year. Only took a few centimeters per year to rearrange oceans over hundreds of millions of years. In the dark, light still arrives from distant stars, and Earth still returns energy outward as infrared, a quiet planetary exhale that never stops. In that exhale, the atmosphere's molecules continue their disciplined work, absorbing, emitting, scattering, always following quantized rules that are older than any coastline. Only took a handful of greenhouse bands to make the difference between a frozen world and liquid seas. The tiny worlds inside atoms keep their private motions. Electrons hold bonds. Protons and neutrons hold nuclei. A rare nucleus tunnels and transforms, releasing a particle that will slow collide and become heat, then fade into the general thermal movement of matter. Nothing announces it. Nothing needs to. Only took a probabilistic event repeated across trillions of atoms to become time's most reliable footprint in stone. In living water cells continue their quiet chemistry. Membranes flex and reseal, gradients rise and fall, enzymes guide reactions along narrow paths, and metals in their active sites shuttle electrons as calmly as iron in ancient seas. Oxygen lingers where it is produced and where it is carried, sometimes abundant, sometimes scarce, still shaping which molecules persist and which are quickly rewritten. Only took a slow accumulation over deep time for a trace gas to become the background of breathing. The narrative lets the deepest mystery remain. Unforced atoms can be described with precision, and yet their foundations still allow questions about measurement, about probability, about why the constants have the values that permit stable matter at all. These questions do not disturb the surface scene. They sit behind it like distant starlight, present, quiet, and not urgent. Only took knowledge reaching far enough to reveal the horizon behind it. The world continues without needing a final word. Water keeps moving, rock keeps bearing weight, air keeps exchanging heat, time keeps passing in one direction, and in that steady continuation the smallest rules remain exactly what they have always been. Not simple, not exhausted, and never finished, yet dependable enough to hold a planet together, and gentle enough to let it rest in its own long, lawful sense.